help moderate. So if you have technical questions, please direct them to him. And if you have scientific questions, our host is disabled attendee screen sharing. Need help with that?
Let me look into that. Oh. Could you try again now?
That just worked fine. All right. I'm just hoping everybody can see my screen?
Yes, Casey, we can see your screen. We can see your PowerPoint.
Excellent. Okay, well, good morning, everyone, and welcome to Thursday of this week-long Interstellar Probe Fall 2020 workshop. And we're about to head into discussion of the many different kinds of astrophysical science that can be done by the Interstellar Probe mission and what we should be putting in the study. And this is an interesting discussion because it's polyglot. There's lots of different pieces of science that can be done. And it's going to overlap with the next session I'm going to lead, which is the dust science, as well as astrophysics often includes things like the nearby interstellar medium, which some of the helio folks want to talk about. And it usually includes exoplanets. So there's a lot of overlaps. And there is no intention at all in this discussion for us to try and overlap in any sort of competitive way with anybody else. What we're trying to do is make sure we cover all our bases. And what you're going to hear from me over and over again is the goal of this presentation, what I've been told and directed to do, is to present to you what we currently have captured in our science traceability matrix, of written down and saying what are the things that ISP should be doing on its long journey out from the solar system to the nearby galaxy. And to see if we have said those properly and to make sure we haven't missed anything. That if the collected wisdom of the audience here has any great ideas for what we should be adding to the STM, we're actually going to work through it a little bit. I'm going to put you guys to work while I have your attention. Then we should add it. Guys should speak up. People should not be shy. We have a small enough group. I'm happy to take points raised while I'm talking. If I will leave this up to James. If you would prefer to see it in the chat and there's no Q&A, we can do that too. Either way is fine. Okay, so all that being said is that I want to make sure that everybody understands that this is not just a presentation by me. It's by a small and focused group, including people like Mike Zemkov, RIT, and Andrew Pape of Berkeley, Jamie Zalei of Princeton, Mihai Horiani of Colorado, Bruce Drain of Princeton, Chaz Bleichman of JPL, Viola Sterkland of Bern, Annie Chantel of Sorbonne, Rosine Lamont of Paris, Jamie Bach in Caltech, and of course our APL leads. And of course, also Alice Sokoperis of APL. And so there's been a lot of inputs from a relatively small focused group, and we're opening it up now to expanded discussion with everybody. That all being said, astrophysics science spans both what is currently called the baseline threshold missions, which are heliospheric directed instruments and studies, and the augmented missions. So how can it actually be in the baseline threshold? Well, some science like the makeup of the very local interstellar medium. What is the nearby galaxy, the dust and the gas between the stars, is going to be, is astrophysics, as well as if the helio guys want to claim it's the helio. It is astrophysics, understanding the galactic interstellar medium. And we can do that using the dust analyzer, but also using the neutral gas spectrometer that is flying in the baseline payload. There's also background work that can be done. The UV EBL, extragalactic background light, can be measured with the Lyman alpha spectrometer. So again, this is some good astrophysics that can be done even with the baseline, purely heliospheric focused instrument payload. But there are also dedicated instruments we're talking about in the augmented payload, like the planetary optical camera that can do optical background work, and the Vizier mapper, which I'm going to go into in some detail, which can do the certain map and actually tell you the composition of the circumsolar dust debris disk, and also tell you about the Vizier, the extragalactic background light, what's going on from the light from the first stars and dusty galaxies. Those would be very exciting to have the augmented payload, and you'll hear about that in detail later. I will discuss in summary slides to present you the science potential for those folks who may not have heard this before. Those who have attended our webinars and heard us talk about this at meetings, it's going to be familiar. But then we're going to get into the instrument requirements and ops issues a bit. And trust me, I know this is somewhat difficult, even when we're all sitting together in a room. Of course, we're doing this remotely. We're going to do our best to get input from you in the Google Docs and to familiarize yourself with the Google Docs if you have an idea or two that comes along later. that it's easy for you to input that and for us to pick it up. I'm going to list the workshop posters related to ISP astrophysical science. As I said, I'm going to put everybody to work a little bit at the end of this discussion for about 20 minutes, hopefully. Talk about the science potential, what's in the current STM. I also know that just thinking through and writing these slides, I realize there's a few things that we haven't really done very well in the current STM. And those are things like UV and optical background science, as I mentioned, with the Lyman alpha spectrometer, planetary optical camera. We also, I just was talking with Sunny about this right before starting here, is I realized that one of the things that we're charged to do is to actually turn around after we go to do tomography as we fly through the solar system's clouds, but also to turn around when we're done and we're outside of them, turn around and take a wonderful look back picture of the solar system in the mid to far infrared. But it occurred to me, there's also going to be planets if we're sensitive enough. And that would be a fantastic picture with the sun in the center, the big sooty dust cloud around it, and little points of light. Maybe just from Jupiter and Saturn, but it would be nice still to have those there. So we'll talk about that. Now, science potential. There are studies that we thought about would be fantastic science that would really help be aided by ISP being far away from the Earth, like microlensing, but we just don't know how to do it given the current rough mission design. It would just take way too much fuel and 3-axis point stabilized. In order to get a good microlensing light curve, you need to visit your target once or twice a day for a week or two. And that'd just be very prohibitive. Instruments, we're going to talk about the suggested strawman payload. Ops, we'll talk about spinner, no spinner. We'll talk about the distance of observations, the data volume. And then finally, I'm going to introduce you to the Google Doc. We're actually going to walk through it a little bit. Okay, so next slide. So you heard this from Pontus on Monday. There's a lot of science that can be done with interstellar probe. Of course, the main science is to actually travel through our heliosphere as a habitable astrosphere. I'm not sure if I've lost mine on the left. I'm not sure. There it is. And actually sample the particles and fields and understand what happens at the interaction region between the heliosphere and the nearby galaxy. And these are actual examples. These aren't cartoons. Those are cartoons. These are real images of other stars as astrospheres having shocks when they're hitting, and these are probably stars that have very thick winds moving through very quickly through their local galactic region. And that's why you see these shocks so prominently. But still, we know they're there. We have evidence. And we're going to take an infrared, if we get it, we're going to take an infrared mapping spectrometer. We're going to take a dust analyzer through this region for the very first time. And we're going to measure things that have never been measured before. And that's fantastic astrophysics right there. Then we're also going to take those same instruments into the nearby galaxy. And again, not been done before. Everything we know about the nearby galaxy has been done by spacecraft localized near the Earth and inside the Zodi cloud. So just getting outside the local obscuration and taking a dust sampler right to where we can actually measure pieces of dust in situ is just going to be a fantastic science return. There's plenty of pure astrophysics opportunity with remote sensing. This is a very nice picture that promulgates the idea that Big Bang happens over here. It takes a while for the hot plasma to eventually become recondensed and the universe, and then stars in the neutral medium, the recondensation, the little asymmetries that are put into the universe by quantum fluctuations of the Big Bang eventually become megaclusters of galaxies. Galaxies form stars in them. The stars have put out enough UV that they do what's called reionization. They take the neutral gas that was dominating the universe and they reionize it to the dominant plasma that we see today. And then eventually you get known love, you get the 10 to the 22 galaxies and, stars and 10 to the 11 galaxies we think are in the universe today. Very, very sweeping. You just heard 1 minute worth of cosmic evolution. The interesting thing about this whole picture, and when I walked you through it, especially planetary and engineer guys, is that all the light that ever shone was ever created by the first stars and the first galaxies up to the present day stars and galaxies that have evolved from that has been rattling around the universe. Some of it's been absorbed and re-radiated by dust, but it is out there and it is a beautiful background. And it tells the story. You can actually tease apart because as you look back, the optical light, let's say our sun has got its maximum radiation at 0.55 microns or 5,500 angstroms. As you look back, that gets redshifted. Distance is time. You can look back towards earlier and earlier in the universe. And so we can actually look at the signals in the background, the diffuse background, which I have my cursor, and we can actually tell different epochs should be producing different amounts of redshifted light. And so we can get a spectrum of this background. We get a clean spectrum once we're outside the local cloud. We can really try to tease apart and understand the progression as the first stars and galaxies formed and came to be us today. And that's a very exciting prospect. And that's promulgated by getting an infrared instrument outside the Zodi cloud, as we'll talk about a little later.
Casey, we have a question in the chat. Is that okay if we do that during the presentation?
If you think it's important to ask right now, yes. Go ahead.
Yeah, so we have a question from Isaac Ashland, I think in reference to the plot on the left, asking, are we planning on aiming for any particular location of the bow shock?
The current notion is to go about 45 degrees off what's called the nose of the bow shock. And that would be best because, as I'm going to show in a little bit, we don't understand. These actually illustrated. This is almost a bubble. See, this is almost a circular spherical shape. This one is beginning to get much more distended. We don't know whether our helio sheath, we think we have models, but we don't know for sure whether we look like this one down at the bottom right, which is the blue one, which looks almost spherical. And that's a case where the star's wind dominates, or whether we're more dominated by, the wind doesn't dominate, but the magnetic field structure and the velocity through the local medium, and we get more extended, less spherical structures. So our heliospheric colleagues and experts are telling us the best way to go is not actually straight down the nose, the ram direction, but to go about 45 degrees to that, to be able to distinguish between the different models of what our heliosphere and heliosheath and pause and our ram, the shock, if you will, construction or morphology looks like. So that's a very good question. Thank you. I'm going to move on. So there's really exciting science. We know there's a shock. Well, we don't know if it's anywhere near as pronounced as this. We think not, because we would have seen it really clearly from telescopes from the ground, but we know there has to be at some level. The other thing that we can do with astrophysics is all the objects that you hear from planetary, I look at them, I study solar system formation evolution. KBOs, comets, asteroids are all relics from how you built the planets. They're all leftover pieces, pieces that if you want, failed miserably to become the planets if that was your goal in life. But they are dinosaur bones of solar system formation. So if one looks at them without those eyes, the planetary science that Kirby et al. Want to do is we highly support that because it tells us more about how we got here and how the planets got here. And those objects formed from a baby protostar plus dust and gas in a circumstellar, in our case circumsolar disk that eventually started clumping just the same way that stars and galaxies clumped from the initial Big Bang relatively smooth distribution. The same thing happens in rotating disks around protostars. And how that happened is still a matter of, we're learning and debate. We learned a lot just from flying by and studying MU69. So more is better. We need to get more examples of this. We also need to understand how our dust disk compares to other system dust disks, and I'll show that in a minute or two. And can we actually tease apart how our evolution happened by looking at other systems that are in different stages of their evolution? We can't go back in time because I and other people have failed miserably in making a time machine so far, but we can go back in time by looking at other stars that are early in evolution and see how they're behaving. Next slide. Oh, I'm doing the slides. Okay, so you all have heard this. ISP is going to go out on this fantastic journey from the Earth, which we know and love, out to orders of magnitude and go out into the nearby galaxy. What we often don't talk about in this when we're showing this picture is that, okay, we go from the planetary region, we're going to go through the heliosheath and the heliopause, we're going to go in the nearby galaxy, and then stars happen. Well, there's lots of physics going on when stars happen. There's the ISM, there's stars all over here, there's the extragalactic background line, as I'm mentioning, from all the galaxies and stars ever formed. There's a lot going on here that kind of gets jammed into this last little order of magnitude. So we're going to talk a little bit more about that now. Okay, so as we fly by the planets, and as we do this fantastic Kuiper Belt flyby, and we're also going to be flying through the solar system's sparse inner outer dust belts created by the asteroids, the inner part of the dust belts, and the Kuiper Belt objects, the outer part. This part is just brand new and just been discovered and detected by New Horizons dust counter. And I want to point out, it's a dust counter, it's not a dust analyzer. It simply just said, here's a piece of dust I've been hit by, and gives you an estimate of mass and velocity. It does not give you composition. We know that these kind of debris disks, circumstellar debris disks happen. Here is a montage of 15 different disks as seen by Hubble. And most of these are young stars. I should point out that if you can image them relatively far away, these are all Kuiper belts. Asteroid belts would be sitting down right on top of the star at this resolution. But it's fantastic to see all these systems have Kuiper belts that are with dust that's lighting up. And so we know it's very reasonable for us to have one. We don't think ours is anywhere near as dense as these. A lot of these are either from very young stars that are still forming planets, or from systems that have just had collisions, grinding asteroids or exploding comets, things like that, that are putting out an enormously large amount, or forming planets, and what you're seeing is construction dust. So that being said, is that we expect one around ours. And the relic dust that we have tells us about how we formed, and also about the processes that are still making the dust today. So I'll go to the next slide. I mentioned this. This is actually New Horizons' flight path. This is New Horizons' dust counts versus distance. And this is the, what you're not seeing here very well, is this is actually data driven by Helios and Pioneer 10 and other missions that have gone in the regions between the Earth and Jupiter and have measured the dust. And the dust from the asteroids comes down really steeply. Now, this is a log plot, and pretty much comes down and would have zeroed out, except it doesn't. As you see, this data points are really plateauing. And the reason why the asteroid contribution doesn't just, the actual data doesn't follow the asteroid, is there's a second population. And the second population is the Kuiper belt and the source. And the Kuiper belt dust is being formed at somewhere between 30 and 50 AU. It's spiraling in, and it's actually populating the Kuiper belt regions all the way into about Saturn's with dust. That's pretty exciting. Here's a piece of astrophysics, or if you will, very local planetary dust and astrophysics that New Horizons has done. What's going to be really interesting to see is to see whether, when New Horizons gets beyond the Kuiper belt, whether this falls off as predicted. In other words, does our dust disk have an edge because the Kuiper belt has a rough edge, or has a limited extent? Okay, let's go to those bow shocks in a little bit more detail. Thank you for that earlier question. Here are a beautiful image. This is in the infrared. This is actually in the UV. And you see that there's, this shows better. Here's one bow shock that is very, what we call cometary, and here's one that's very spherical. And this one we think is velocity and magnetic field dominated, and this one is a stellar wind dominated. All these are pretty big, bright stars. They're light type stars, really big red giants, or they are big O and D stars. They're not G stars like our sun. So that's why they're a bit acting out. You can see them very well. And in the lower right, you can see these are two models for how the sun would be if it's solar wind dominated. Again, I think I've hit on that point. So this is going to be a fantastic piece of science that the heliospheric experts are going to push and are going to understand and going to produce from ISP. But then we as astrophysicists are going to try and connect it up to everybody else that we see in the galaxy and try to understand and what that means about how our star is behaving and evolving in the galactic environment. Okay, once we have gone through the shock and we understand what that is, then we're going to fly into the nearby cloud, into the nearby local galaxy. And it's easy to think is it's just kind of a rarefied uniform structure. Far be it. Our best understanding from work, and this is actually a picture from the IBEX mission, is that there is structure even in the local cloud, that we are actually on the edge of a dust cloud, and we actually might be going into a dust poor region in the next few thousand years. There's predicted structure. This is from remote sensing observations. This is very exciting. As I'm going to talk about in a little bit, actually probably in the next session, the remote sensing observations don't seem to agree with measurements we get of interstellar dust in our system, collected in Jupiter and Saturn, deep in our heliosphere. So there's a little bit of a grain of salt. Not that we want to actually go out and kick the tires. We need to go out into this local cloud and sample it, and then make those connections. One of the things that's very interesting to think about from an astrophysical point of view, I think it's Eta Canis Majoris or is it Epsilon? It might be Epsilon Canis Majoris, is the nearest O or B star. You can check me on this. That's putting out a huge amount of UV, and this star down here is, it's not this star. It's a different star. This is a star I'm studying with Chandra to look for a bow shock. It is down around here, if I recall, and it is putting out the single most amount of UV in our local medium. It's driving a lot of what's going on in the ISM in terms of ionization and plasma structure. So we've been reminded by that in previous workshops that there's one, you should go look it up if you want. I think it's Epsilon Canis Majoris. Okay, but wait, there's much more. We've just talked about, in this previous picture, I'm showing you we're making those baby steps. We're getting out of our solar system. We're getting into the local galaxy. That's good enough, isn't it? But wait, there's much more. We are part of a very big galaxy, and we live 2/3 of the way out in the Orion spiral arm. And There's, we think, 100 billion stars in this system. We're just one of them. Very nice one, thank you, I'm not complaining. But this is a system that we think is 13.7, excuse me, the cosmos is 13.7 billion years old. We think the galaxy is about 12 billion years old. The sun is only 4.56. Let's round it up to 4.6. The sun is relatively young. And it's in spiral arm, it's expected, it's a relatively newly formed star. So there's lots going on from between us and the center of the galaxy. And one of the things to think about is what we call galactic chemical evolution. We'll touch upon this more later. Is that if this is the galaxy and the galaxy is densest here near the core, where Sagittarius A star, where we think we have a million solar mass black hole, you would expect that stars would form and live and explode and die much more and be much bigger where the galaxy has the most density of mass, and that would be near the center. So you would expect many, many stellar cycles there, and you'd expect a lot of burning hydrogen and helium to heavier atoms, and what I'd like to call fusion ash. So you'd actually expect what's called, astronomers call metallicity. You'd expect a lot more iron and heavier elements in stars here than you do out in stars here, where things are more rarefied and evolution was slower. So this is a big thing that galactic astronomers would actually like to measure. By taking ISP, it's a small step, but taking it actually out into the ISM and directly measuring the atoms we get in the dust there, that's going to give us a handle. What it'll do is give us some ground truth, what we've only measured remotely at these different kinds of elements. And then this is actually, if you want to think about this, remember I talked about the light from the first stars. This is a picture. I always love looking at this picture. This is a real picture. This is not our rendition by Hubble in a deep field of some of the 100 billion island universes, galaxies that we know in the cosmos. And they just look like beautiful colored shells on a beach to me. And it's amazing to think, and this is the light you're seeing from if you were to smear this out, or many of these are very, very faint points, and some of them are going to be unresolved as they get fainter and fainter, and they're just going to add up to be a diffuse background. And that's the background I was talking about before. So I always keep this in mind when people are talking about the cosmic background and say, yep, it's really there. I just talked about this a little bit more. I think I will, because I talked about it earlier, I won't go into the details much more, but I will say this. Here's a plot of wavelength or frequency, and optical is here. So this is visible light, infrared. And these are the backgrounds expected from formation, universe formation, starting with the Big Bang, and then surface of last scattering as electrons and protons cool off and recondense into hydrogen atoms. Eventually stars and galaxies form, you reionize, and as I mentioned, and then you get to the present day. These are the backgrounds that are created by those different processes, okay? This is a nice model, but one of the things is I worked on the Cosmic Background Explorer project. So me drinking from my Kobe cup. That's how I got into astronomy. And what Kobe did was it measured precisely the cosmic microwave background that came from the Big Bang explosion. And it has a characteristic temperature of 2.73 degrees Kelvin. It can fit it very well with the black body. So we know that this pervades all of the universe. If you guys want to go and watch it tonight, turn on between some channel that has no signal, and 1%, 3 degrees over the 300 degree Kelvin of your room, 1% of that noise is actually background photons if you want to go watch the Big Bang. Infrared background, mostly dominated by dusty early galaxies that down converted a lot of the optical light from the first giant stars into absorb the light, heat it up, and re-radiate it as infrared radiation. So this tells you a lot about the first galaxies and their stars. The optical is dominated by what's out there mostly today, what we call the last few, redshift out to a few, and then UV as well. And so these different bumps, if we can poke at them, and we can do it outside our local obscuring zodiac cloud, you can learn a lot about how the cosmos formed, how we got here in a different way than galactic local formation. I like to say when people ask me what I do for a living is I study the local cosmology with solar system formation, as opposed to the universe's cosmology. So this is pretty exciting that we can do this, or try to do this. And this isn't just pie in the sky. This is IRAS and Kobe's observations of the sky in infrared wavelengths. So going back, this would be these wavelengths in here. And when you look at it, what you see are two things. This is the galaxy dominating. And this, what looks like the Z of Zorro, this is the ecliptic plane. That's the zodiacal cloud we're going to talk about some more. This is the dust cloud created by those asteroids and comets and Kuiper Belt objects. Because this isn't a galactic plane, it looks like a Z. And this is the same stuff that if you go to a very dark sky at night and you look after the sun is set, you see this beautiful, it's almost a parabolic arc of light. And what that is sunlight coming over the horizon, scattering off the dust disks, coming back to your eye. It's pretty amazing to see. It's easy to see from Hawaii when you're observing out there. Okay, so I think I've mentioned this a lot. I think I'll just keep moving through that slide. This is, I've said it in words, this is actual demonstration. This is the estimated EBL. So this is the extragalactic background light, this red curve here. This is the signal from the ZODI at 1 AU. This is what we live in when you look at the sky. So you are totally dominated by the local. It isn't until you get out to 3 AU, and then 5, and then 10, is when, the, if you will, the local sky begins clearing out. It's sort of like thinking about the fact that right now I'm talking to you, but I'm looking out my window and it's a bright sunny day. The stars are out, they're there. You just don't see them because they're dominated by the sunlight that's scattered off the atmosphere, the dust and the gas in the atmosphere, and you can't see it. But that's why if you take a spacecraft up through the atmosphere, suddenly the sky becomes black once you're above the atmosphere. Even the sun is out, it never goes off, but you can see the stars. It's the same kind of effect. We're basically dominated, and the signal from the EBL is overwhelmed by the local bright emission from scattered sunlight. So if we can go out and with ISP, and you'll notice we only need to go out 10 AU, we don't even go 100 or 1,000. We can do an awful lot of science. We just get and look in near infrared and the very red light, so very red optical to the near infrared. We can do a lot of science right in here, plus more if we go farther out. And one of the very interesting things in recent news, besides, hey, this sounds like a nice idea, current estimates, people putting together their best measurements using Hubble and Spitzer and COBE and discrete photometric observations in small patches of the sky. Right now, as far as we understand it, these are the models of what light should be out there. The curves, colored curves, the points, triangles, squares, etc., are measurements. Right now, there's too much light, and we don't understand how the stars and first stars and galaxies formed and evolved. There's a problem. There's tension. And that's good. Gives us a reason to do something. So how would we do this kind of measurement besides the heliospheric package? Here's what we call a vis-near concept. So the vis-near standing for visible near infrared. We would actually take a small sat design by Mike Zemkov of RIT. And now this is a study. We would take this is an example in a straw man. We should say this is not chosen at all. But this is an example of what you could do. It's a small sat design. It would weigh about 5 kilograms. It's designed to be a small sat in Earth orbit. And he has adapted it to ISP's needs. And it cools itself passively by having 3 nested optical shields. Light would come into a primary mirror. So light comes in here, rattles around. Here's your beam path if you would like to see it. And it's going to get split into far infrared and near infrared. We should be careful. It really should be Vizier because it's going to actually do some mid to far infrared work too. And it's going to have a 0.5 to 15 micron imaging spectrometer capability. To compare that to Lisse on New Horizons, Lisse went from about 1 to 2.4 microns. So this could do Lisse's resolution. We've also checked it. Can do Lisse resolution and at a much bigger wavelength regime using modern technology. We would like to also put in 4 far infrared channels, big fat pixels, single pixels, and those would just map the coldest dust in the zodiacal cloud. Those Kuiper belts I was showing you that are around other stars. We want to do both. And we also want to have this capability because this allows you to do that EBL. So I don't want to dwell on this too much, but because it's in the STM, but I want to point out 0.5 to 15 micron spectrometer. For bands, we fuss over exactly the numbers, 40, 60, 100. We might actually do 30, 40, 60, 100, right? And the 150 is probably not going to happen. As you get longer wavelength, it's harder to get good sensitivity unless you're very cold, and there's some issues with active versus passive cooling. We can get down to about 10K easily. 4K is listed here, would take active cooling and take mass and power. We're not sure we have. Point out that the interplanetary dust science, you can do most of that. You have to get outside 70 AU, so that's one of the reasons we want to go out to a few hundred. If we want to get that look back image of the whole ZODI cloud, we need to be out 200, 300 AU. The extragalactic background science we were talking about earlier, once you're outside 10 AU. So this is something you can do relatively quickly after launch. You can get a much better estimate of the first stars and galaxies. That's pretty exciting. And then in between, of course, there's the KBO flyby science, this instrument will be able to do what Lisse did at New Horizons, at Pluto, excuse me, on New Horizons. And that's pretty exciting. The other thing it will be able to do is what Rex did, which made some temperature estimates of the backside of Pluto and MU69. It did that in swaths or kind of chords across the bodies. We'll be able to actually get maps. So I like to think of this instrument as Lisse Plus and Rex Plus from New Horizons, which is pretty exciting. There's some ConOps issues. We'll talk about those a little more in detail. The data volume, it could be tough if we're trying to map the whole sky. And so you want to do that whole sky mapping quickly when you're near the Earth, and you win by 1/r². So one of the good neat things, the reason I was pushing on it, is you can do most of your EBL work when you're out past 10 AU. You don't have to get too far. That's Saturn's orbit. And so you can do a lot of the extragalactic background light work, mapping the whole half of the sky. You can do it while you still have high data rates. And so then you can wait until you do the flyby. Then you can wait until you do the look back image. And so you can actually keep the data volume from this instrument moderately low. You do have to ask the question how you would actually map the sky. So it sounds like we would like for this instrument to be looking at an angle to the ram direction if we're on a spinner. And we let the slow spin, actually let us to cover the sky. To watch the time. I'm going to move on a little bit, but I want to point out here is we've actually done a lot of modeling, Andrew Pape especially, along with Mike Zemkov, trying to figure out what wavelengths one could look at. And this is the total signal. This is the signal from the galaxy and extragalactic background light, and this is the ZODI. How far do you have to go out before, basically, when does the red curve, due to the solar system ZODI dust, drop down between the signals that you're looking for? And you can see it happens around 10-ish AU for 10 microns, and it happens, as Mike likes to put it, we're done by 70 AU, and it happens, again, even for a little bit shorter than 10 AU at 100 microns. So this is our argument and why we just need to get out there a little bit, out to Saturn, get this instrument, and you've done a lot of good cosmic level or cosmological astrophysics. Okay, that's the very brief introduction I wanted to give you. What I want, now I want to list the posters, and what I want to say is that this introduction, which I gave in a webinar a few weeks ago, doesn't really cover too well the physics of the ISM. One is that I'm not an expert on it, but two, I'm realizing after looking at all these poster titles that an awful lot of the posters, I think especially from some of our younger scientist members, are on, these are astrophysics related posters, PAWS in the interstellar medium, very local interstellar medium particle environment. Peculiarities of the interstellar dust distribution in the heliosphere. A lot of these are, if you go look through them, have to do with what's going on in the local interstellar medium, elemental abundance of the gas and dust in local interstellar cloud. And one of the things I think the low-hanging fruit, if you will, for this group, would be to help us improve what we currently have in the STM, discussing what are our science goals for the interstellar medium. Now, I'm going to walk you through some of them. There certainly are some there. The questions I have for you is, are we missing anything if I'm pointing at this one topic? And or can it be written better? And because I think it's going to be very hard to wordsmith in a committee, all meeting electronically, let's not try to do that. But we will do is I'm going to ask you after we go through the Google Doc, is if you have better ways of saying these questions or suggestions, please give them to us. Okay, so that's just, I'm highlighting what I thought and what this workshop has helped me realize is that maybe we need to work a little bit more on the astrophysics of the ISM for the astrophysics science cases. Okay, you've heard me say it before. The Vizier spectral mapper would be the prime, if you will, augmented payload instrument for astrophysics, along with an optical flyby camera that can also get us to the optical backgrounds. If the look back camera, which has been proposed, can do that as well, it doesn't just have to look at planets. We're happy if it looks at the sky and has the resolution, a big pixel resolution to actually do some sky mapping. And I've also mentioned the UV imaging spectrometer can do Lyman alpha backgrounds. And those backgrounds aren't necessarily as much, they can be cosmological, they can also just be due to the local, what we call the hydrogen wall, where there's a charge exchange recombination of inflowing interstellar hydrogen and helium hitting the solar wind. It can also tell you something about what's going on at that shock. And it might be telling you there is the interstellar, there's the galactic radiation field. What is just the average amount of light per cubic meter, just the energy density, just coming from the fact that stars are emitting light and it's rattling around the galaxy and getting scattered and rescattered. We know galaxies have diffuse emission, so it will help tell you something about that too. And I want to point out is there's overlapping science. The Isp Dust Analyzer, while I'm going to talk about dust and we're kind of stovepiping it into a separate session, it is giving you the local in situ dust number, composition in the circumsolar, in the heliopause and sheaths, and in the local galactic medium. And what these other instruments are doing is, rather than giving you the local, what you are here kind of measurement, they're going to tell you about the dust that's far away on the other side of the galaxy if you go long enough wavelengths. And we're going to be able to compare and contrast what we see in the very local galaxy to what we think we see much farther away. And that's a very exciting possibility as well. Okay, again, we're going to talk about this, the Google document. I can come up with two things, the operational requirements and constraints. The first that we should definitely be thinking about, there are plenty of others, and I would love to have your input on these. Spinner, no spinner, angle versus ram direction. The astrophysicist, if we could get it, we'd prefer a no spinner that could map the entire sky at our leisure. And if we had infinite data volume, that we'd take as many sky maps as we could. Well, that's not real. And one of the things I'm going to keep harping on is we need to do what fits within the mission constraints. If we are going to have limited data volume, we have to be careful how we do our sky mapping. So, and as I've already pointed out, if we can take sky maps sooner and get good quality science, that's what we do. We can work with a slow spinner. What I'm hearing that if the helio folks want to spin, they'll spin about 1 RPM. The question is, if that's slow enough? 1 RPM is still 6 degrees a second. That's quite a bit of spin. That's quite a bit of smear. So we have to think about whether, for astrophysics, we make some recommendations. If we can't live with 1 RPM to do this, a lot of our science, we may have to ask for some 3-axis stabilized no spin modes. It won't be the majority, especially when we're much farther out, 100 to a few hundred AU. But we might actually get some quiet times that might be good enough to get the science we need. These spinning issues could also be ameliorated with a scan mirror or with nose mounting, as we heard Carey and the planetary folks suggest, or very short integration times. But the problem with the short eye time is that we're not looking at bright things, we're looking at really faint things. So this probably isn't going to work. We would like a cone angle versus the ram direction. You don't want to look straight down the pipe because you actually want to actually scan the sky. So we'd want maybe 20 or 30 degrees off the ram and then revolve around a cone and let the spacecraft move that cone through the sky. We do, however, we don't want to have that cone angle greater than 90 degrees because then you start looking back towards the sun, you get issues of light scattering into your telescope and as well as heating. So we know we don't want to do that. So that's defining your problem. You want your cone angle somewhere between, let's call it 20 degrees off the ram out to probably about 70 at most. So somewhere in there. The heliocentric distance, what planetary astronomers call R sub H, R heliocentric, of these observations. Well, if we want to do the ZODI, we're going to do that from 1 to 100 AU, the solar system dust cloud. If we want to do a look back image, we're going to go out to 500. If we want to do the extra background light, all we need to do is get out to 10 or 30 AU. We can do it really soon. Data volume, I mentioned, can be very high for complete hemispherical sky maps. You got to be careful how much often you do that. And you already heard me mention, do them as close as Earth as possible, take advantage of all those bits per second we have when we're near the Earth. Okay, I've walked you along. It's now 12:13, so we're taking about 40 minutes, and thank you for your attention. The goal of this workshop, and we're about to go to the Google Doc, which I've constructed for you, is to familiarize everybody with the current science engineering plans. You just heard me give you a brushstroke idea of the science, and collect ideas for improvement. The best option with this remote Zoom meeting format required by COVID in fall 2020, we think, is this Google document. And I'm still learning how to use it, and there were some times where it was a pain in the arse to try and do cut and paste and replace and last night. So I'm not totally thrilled with it, but when I think about it, we are meeting remotely. All you're hearing is me talk right now. If we open up the floor for everybody to talk, which I would love to do, in a Zoom format, that you're going to get a lot of collisions and the signal is just going to get lost. So the best thing we can think of doing is send everybody to the Google Doc and having you literally type in as we're talking. Some people can go ahead and chime in one at a time, but the rest of you, if you have ideas, please put them into the Google Doc. We understand that STM workings are even difficult in the committee format. Here we have a remote format. We need your creative input, especially just brainstorming, or if we have something that's so obvious and we've missed it or we misstated it, we need that. We must work within current mission design bounds. So no teleporters, no warp drives. No, you can't add 1,000 kilograms to this mission. It's not going to happen. We're doing real technology that can launch by 2030. There is no wordsmithing required at this point. If you want, you can, currently, if you think something's been misstated or can said better, please put that in, but that's not what we're driving towards. And especially don't bother editing other people's work right now. We're looking for that creative idea that's an input, and then we'll clean it up. And the other thing I want to point out is the Google Doc isn't just for today. It's going to be up for weeks after this meeting. It's a living document, and we want you to, that's why I'm going to familiarize with it. We want you to go there, and we're going to see how this works, because I think some of the other groups haven't tried this. So I'm going to break out of this, and I'm going to bring you right into, so this will work.
Casey, I also posted the Google document link into the chat.
Yes, please, if everybody could go there. There's a question. Yeah, if you can go there as well as watch what I'm about to walk you through the Google Doc. And what just transpired before was my kind of introducing you to the science, and for those folks who had never seen it before, the possibilities. And this is where I'm gonna push you to work a little bit, if you don't mind, a little bit of classwork. So can everybody see the Google Doc? It's okay if you want to go ahead and
yes,
unmute.
Casey, we can see the Google Doc on your screen.
Okay, and if folks want to unmute and start talking, we'll see how this works. So here's the Interstellar Probe Astrophysical Science Google Doc, which I also semi-facetiously said, take humankind's first Vizier spectral mapper outside the zodiac clouds and go to town. That's focusing on one instrument. All these instruments outside the zodiac cloud are going to do fantastic work. I can't wait to see what the optical camera is going to do as well. Kirby pointed out to me, if it's nose mounted, it might not look it might not be able to map the whole sky, but we'll think about it. There may be workarounds. So again, the main goal of this workshop, and you're going to see some repetition because I wanted to have everything in this document. If there's one resource you need to come back to, and I know how this works, it's very possible you'll never look at this document again after today, which is one of the reasons I'm going through it with you today. But it is very possible that if you might come back to it in a day or two with an idea. And so I've written down a lot of what you just heard again and put it right here. So my apologies if there's some repetition. So the main goal of the workshop, familiarize you, the community, with the STM I'm about to show you, and collect ideas for improvement. We understand that's difficult. I think you just saw all this. So all this being said, here, in all its living color, these are subsections. I'm not giving you the whole STM. There's more columns over here, which you don't necessarily need. I'm actually going to walk you through the different questions that pertain to astrophysics that are currently there. So I hope this works. Please feel free to start, tell me if you're falling asleep. So the first section is astrophysics, understand the composition, evolution, thermodynamics of the nearby and distant interstellar medium. It's important to point out that nearby would be something, for example, that the dust analyzer can sample. Distant is what remote sensing, what your infrared spectrometer and your optical camera can tell you. So the first question, major question we can think of, are what are the properties of dust in the ISM as traced by reflected starlight, and what do they tell us about the dust's origin and evolution? What we're actually going to do is measure the spectrum of the near infrared diffuse galactic light. We clearly separated out reflected starlight from thermal emission from the dust, and we did that because it's different instrument measurements. So in the STM, sometimes you have to split hairs like this. You are supposed to try and just keep things to one question per box. So we could have asked, what are the properties of dust in the ions traced by reflected starlight, and what are they in thermal? We could have put these both together. That's why it looks like there's a little bit of redundancy. Here you see the statement of what we will be measuring, and then here's the actual numbers. What kind of resolution you need, what are the wavelengths, and if you think there are different wavelengths or regimes, or there are more measurements that we're missing, feel free to tell us about them, put them in here. I would ask that you highlight them in a different color so it's easy for us to pick them out. We'd also like to know, once we're in that galaxy, in the nearby galaxy, what are the properties of the pause in that galaxy? We know that when we look at external galaxies, that some of them light up beautifully in the PA lines. And folks who don't know what PAs are, PAs stand for polyaromatic hydrocarbons. If you've ever smelled a mothball, you're smelling a bunch, basically PAs are a bunch of benzene rings stuck together. Or as my old chemistry joke used to go, I like to think of dimethyl chicken wire. They are just a whole bunch of rings. They come from everything from 2 or 3 or 4 fused rings all the way up to graphene, which can be a huge number of sheets of rings stuck together. And PAs are ubiquitous in the universe. They seem to be easily formed in the very thick winds coming from red giant stars like Betelgeuse. I like to think of them, they're like soot, and they are also in soot, by the way. I think they're a little carcinogenic, so don't go sniffing your slit too much. But they are a very stable form of carbon. They are extremely good at absorbing starlight and re-emitting it in the infrared. And that's the way they're detected very easily. They have very strong lines. So we see galaxies lighting up in these things. So we're going to know, is our galaxy also lighting up? And we can't tell very easily because we're immersed in them. But once we're out there, can we actually sample them with the neutral gas spectrometer, with the dust analyzer, and can we compare that to remote measurements? Next question for the ISM, in the very local ISM, is the very local ISM material characteristic of ISM material of the galaxy as a whole? And this is a case where we're trying to go and make a measurement with the dust analyzer, basically locally. But can we then go and use our remote sensors and also other measurements made from Earth to look at other parts of the galaxy far away from the nearby? And apparently we misspelled a word here. We'll fix it. And can we actually look for differences and similarities? Remember that galactic chemical evolution argument I told you about, is that we don't expect the galaxy's ISM material to be exactly the same everywhere. It should have radial variations. It could also have just local clumping of variations like we saw in the estimated remote sensing maps of the very local cloud. It's not uniform. So how not uniform is it? Two other astrophysics questions that are very interesting, and we got actually added in from the particles folks. If we go out and we actually measure isotopic ratios, deuterium to hydrogen, or helium-3 to helium-4, or the carbon isotope ratios, or oxygens, neons, argons, can you actually learn about how these isotopes got there, which has to do with how stars burn hydrogen to helium in larger atoms? Can you actually try and figure out, there are predictions on what these ratios should be in the nearby galaxy? And it's hard to measure these numbers spectroscopically, but if you actually have a dust analyzer, chemical analyzer, measuring these isotopes and having the resolution do that, it'll tell you right away. There's also, if you have really big picture eyes, if you want to go and, if you can measure deuterium to helium-3 to helium-4, you can try and ask, these are species made in the Big Bang. You can actually try to push back from just local galactic evolution to cosmic evolution. This is most likely not going to be the dust analyzer. This is more going to be a gas, neutral gas mass spec. So there's a point at which as I'm talking, I'm realizing we probably should have put that instrument as well as one of our astrophysical instruments. So that was the local ISM. Again, please feel free to help us with that. I want to point out that heliophysics has a number of questions that are overlapping. They've been kind of carved, or not stovepipe, they've been assigned or classified in this STM to heliophysics, but they're also astrophysics. Does the heliosphere create a bow shock or bow wave in the interstellar medium? You just saw me show you a lot of other stars that have astroshocks. So we want to know that. What is the structure and properties of the neutral, the hydrogen wall? And how is that compared to other astrospheres? Again, that's with galactic eyes. So there's overlap. What is the composition of local interstellar material, neutrals and dust?
Casey, I think your screen froze, so I'm going to quickly grab the screen and then you can take it right back.
You do. Feel free. We practiced this. Thank you. Now, again, you heard me say before, is I apologize. I know this can get a little stultifying, but this is actually how one gets a mission. We need to build this STM and make the best science cases.
Casey, I'm going to do it one more time. Sorry, the screen still isn't sharing.
Got it. Go ahead. I'm going to stop share. The other thing I'll say while we're trying to fix things is that this STM is the way scientists talk to engineers for people who may not be experts, who may not have done this before. Is what you're seeing is, this is scientist speak. What is the major science thing I'm trying to, what is the major measurement? What is the goal? What am I trying to learn? And what is unique to this mission that we can do?
Casey,
but then,
sorry, it's still not working.
Okay, well, don't interrupt. Just keep taking the screen away and I'll get the idea. I'll keep talking.
Okay.
Thank you, James. I'm sorry about that. Yeah, we've seen this happen before, audience. Sorry about that. The point I want to make is that you're going from the science, that what you assume, well, the scientist in the audience, that's what we want to do with ISP, to actually, how do you get the spacecraft to do it? And that's when you go to these questions of what is the actual measurement, and then what kind of specifications do you need? And that tells an engineer, okay, I need to build this kind of spectrometer or that kind of camera. And if I can't do that, then I go back to the science and say, I can't meet the STM requirement. What do we do? And the engineer will get, it's asking or looking for one or two answers. One is, well, that they're looking for the scientists to modify that request, or just say is, well, we just can't do it. We're just not going to try. So that's why this document is a bit different than the usual science we do. But this is also how scientists get their instruments and experiments on spacecraft. You don't do this, it doesn't happen. Your spacecraft has to be built by real people and flown by engineers and technicians and spacecraft experts. And so this is how you convert a scientific experiment into a spacecraft reality. Okay, hopefully everybody can see again.
Yes, it's working.
And so, again, I also find this a little tough, but that's why I'm going through this for a reason, is that I know it can be hard to do it unless I'm actually guiding you a little bit. So what is the composition of interstellar material, neutrals, and dust, and how does it differ from that of the solar system? Right now, we don't understand the ISM dust that has been collected by Stardust and the Cassini and Galileo spacecraft doesn't look exactly like what we expect. And stay tuned for the next session. What we predict and expect in the local galaxy from remote sensing. There is a disconnect. It looks like the only things we see, pieces of dust that we see, or the kinds of dust we see in the solar system, seem to be made out of silicates, rock. We don't see the carbonaceous or the metallic materials that we expect to be there as well. So there's something missing, or we think that maybe some of the dust is diverted by magnetic fields. Something's going on. And this also gets the idea that, I'll talk about this more in the dust session, is that when the models I showed you of the helio sheath and the heliopause and the bow shock, they pretty much assume a dustless plasma. We've got helium and hydrogen, and there are ions and oxygen, nitrogen, things in the solar wind that are important, but dust isn't doing anything. Well, there are estimates that dust could be doing up to a third of the energy and mass density there. It could be having a very important role. We don't know. Models can actually do a relatively good job of fitting what's there now, but we know there's dust inflowing into our system. We've seen it coming from the galaxy. And it could be those models have to go back and allow for a dusty plasma, which is a very different kind of physical beast. So anyway, that's why this is important. There's tension. There is a problem that needs to be answered, and it's maybe telling us a lot. Here's also another point. What is the density, temperature, and ionization state of the gas? For those who don't remember, dust is wonderful stuff, but the gas to dust ratio in the galaxy is like 100 to 1. There's a lot more gas and plasma than there is dust in the galaxy. It actually flips. In the solar system, it's about 1 to 1. We've actually thrown away most of the gas that started in our system, mostly hydrogen, in process. We either put it into the sun or we threw it out of the disk, and the Earth certainly is not gas rich like Jupiter or Saturn or the ice giants. Okay, moving on. How is the local ISM modified the secondary neutrals? This I think is a pure heliospheric, so we won't touch on that too much with astrophysics. And then here's another question: how much local interstellar matter is in the form of dust, and how does it interact with the heliosphere? And I talked to you a little bit about the fact that we think that some of the dust that may be coming, one of the answers to the tension between what we think is in the galaxy remote sensing, what we actually measured, only the rocky bits in the solar system, is that the metallic and carbonaceous materials could actually be getting charged and ionized and charged a little bit by photoelectric effect or by pickup. And then because they're more conducting than the rock is, they get actually diverted by a magnetic field that's surrounding the solar system. And they actually can't penetrate into the system, whereas the rock is an insulator and has no problem with that. So that's one possibility. So that's why this is also interesting. This also bears on the question of how did dust flow into our system and form the Earth that we're sitting on today? We'll talk about more of that in the dust session next. Okay, so that's the overlap of the heliosphere. Now let's get to the pure astrophysics and the cosmology. Here, the astrophysics is explore the universe beyond our circumsolar dust cloud. Should probably be the word circumsolar there. And the major thing we would like to try and do is, oops, ooh, did I do that? I think I did. Is to determine the total diffuse redshifted light emitted by all the stars and galaxies in the universe since the beginning of cosmic time. That's why I showed you that picture, because it's kind of a big statement. From vantage points beyond the dominant cloud, the zodiacal cloud. As I showed you, once you get outside the local cloud and all the scattered sunlight and the re-emitted thermal emission from the sunlight, then you suddenly, the clouds part and you can look at the universe in all its beautiful glory. So,
Casey, you can go ahead and reshare. Sorry, it froze again.
Oh dear.
That was me. Yeah.
Go ahead and grab.
I already did. You can go and reshare.
Okay. All right. Hopefully there's still 5 people. Oh, there's 30 people still on. Good. Okay. So what are some of the discrete questions from this? What is the contribution to the total sky brightness from the first galaxies? How much energy is released by the process of nucleosynthesis in the universe? Just combining protons into making helium and then carbon, nitrogen, oxygen, things that make up the bulk of us. That took a lot of energy. And most of these are going to be for the Vizier mapper I was talking about. How vigorous is the process of star formation in the universe? Current estimates are that most of the stars that we see currently today formed at Z of 2 to 3. Z is what we call the redshift. If you look at a photon of light, and again, I like to think about the fact that if you look at a G star like our sun, most of the peak of the emission is coming at 0.55 microns. If you're at a Z of 2, and the cosmology hopefully won't shoot me, 1 over Z plus 1 is the current wavelength. So if you're a Z of 2, that 0.55 gets shifted about 1.5 microns, so in the near infrared. That seems to be roughly if you will, the redshift, the look back times. And also the time goes roughly as 1 over, excuse me, goes as 1 over Z plus 1. So the time those photons are emitted, Z of 2 to 3, and the universe is 13.7 billion years old now. That's what I should have. It was about 4 to 5 billion years ago is when this, and that's about when the sun formed. So the sun looks like we formed during the epoch of the peak star formation in the universe. Our star is probably typical. But there are stars that also formed much earlier than that. So again, this is understanding how star formation occurs during versus either look back time or its proxy redshift is a really important thing to understand. And if we can do that with ISP outside the cloud, that's fantastic. Mike Zemkov and I are on another mission called SphereX, that is that new MidX Astrophysics MidX program, which is designed from 1AU to do that very kind of study, but is inside the cloud and is going to do it in a different fashion. It's not going to simply just go straight and measure the background. So if we could have a SphereX, for example, where ISP is going, that would be perfect. We don't. So these are they're complementary measures of star formation in the universe. And it's really exciting that we can do that with ISP. How does the emission from nucleosynthesis star formation vary as a function of redshift? I kind of just went through that. And very simply, as I think I also promulgated, is that very roughly our sun was formed most likely during the peak. And so I'm glad to know that. I'm glad there was a lot of star formation at Z of 2 to 3. Otherwise, we wouldn't be talking. There's also the question is, what is the total energy released by ionizing sources in the early universe? So when the first stars and first galaxies form and they make their first stars, there's a huge burst of energy that turns the neutral. And the way I think about this is, I think I mentioned before, the Big Bang happens, a giant explosion, just particles everywhere. Everything's ionized, very hot. The universe expands and cools enough so that electrons can actually condense onto protons and make hydrogen atoms, which still dominate the universe today by a lot. But that didn't happen until the universe got relatively cool, and then the hydrogen takes a long time and forms the first galaxies and stars, which are bright enough and hot enough, and they shine by gravitational condensation energy eventually turns on fusion reactions at their center. And that fusion into heavier atoms, as you know, from all we've learned about atomic and thermonuclear bombs in the history of mankind, there's a huge amount of energy released by just a small amount of mass change. I think it's 1 part in 10 to the 3 or 10 to the 4 change in the mass of one of these atoms when they proton and neutrons when they fuse, but it releases a huge amount of energy because E equals mc squared. All that energy from just a small amount of conversion of mass into energy from galaxies and stars was enough to reionize the universe. So it's the dominant species in the universe is a proton and electron. You have to count all the species and all the interstellar media and all the stuff between the galaxies to get that, because we're certainly not plasma and ionized on the Earth and in the solar system very much at all. But it still dominates. Just the same way that the dominant energy, if you remember what I showed you before, the dominant energy source in the universe, if you just take the energy per meter cubed, it's still in the CMB, it's in the microwave background. I showed you that earlier in the PowerPoint. If you go back to this plot here, kind of interesting to think about. See this? See how that peaks above? It's hard to believe that because you would think that stars outshine everything and there isn't that much radio noise, microwave noise, but you have to sum over the entire universe and all the volumes that aren't galaxies and stars. But that's still the dominant energy component. All right, I'm trying not to go on too much. I hope this is a little bit interesting. I find it useful to see the connections when I'm trying to work on things like this. And then finally, what is the contribution from dust-obscured star formation? Those first galaxies seem to be different than the ones we know today. And going back to that plot I just showed you, I mentioned the fact that most of this radiation, and this is what we learned with COBE, in fact, product placement, is that most of this signature is not coming from currently warm things. It's coming from the fact that the first galaxies seem to have still have been very, very dusty. They weren't as clean as we are now. And the dust was able to obscure most of the light from the first stars, which were very different than our star. They were big and they were bright. And they didn't live very long because they had mainly almost hydrogen and helium. They didn't have the other stuff that our sun has, iron and copper and carbon and nitrogen, et cetera. And most of this is coming from re-radiated starlight. So if we can actually tease this apart, we can learn a lot about the early galaxies. So that all being said, I have just walked you literally through everything in the astrophysics questions. I'm going to do the same thing in the dust section. So hopefully you're still there. The items we know and the cases need to be added. I was just thinking through as I was reading all this. I don't think currently astrophysics is doing a good job on the UV Lyman alpha cosmic background. And also should be galactic and cosmic background.
Casey, I think the screen froze, so I'm going to take it again quickly.
Go for it. It is also not doing a good job on the optical cosmic background. There's science to be done there. And as I mentioned, also, I don't think it's doing a good job on the solar system look-back image, just taking a picture of our sun with its surrounding debris disk. And it occurred to me, if this needs to be a simple study, if we just ask Sunny today to do this, if in that look-back image, there's also the planets, even if it's just Jupiter and Saturn, the big boomers, if we can see that, that's a fantastic image. And there's some astrophysics to be done there because that compares directly to what we see when we're looking at other solar systems from the outside. So there are interesting pieces, like you heard me say this before, astrophysical science we left out, they're just not in there. You can feel free to push back if you think of a way to do them that is low resource usage, and I'm just going to list them as microlensing exoplanet light curves. The other things we need to do with this document is how are we going to do these measurements? For example, the spin state, when we do them in the mission. We were also asked to verify the science data volume allocation. We think we're okay with this. Mike Zemkov has done a detailed study, but I would like to hear your thoughts on this if you have any. The fourth main goal we were also supposed to talk about was collect comments on the two example payloads. That would be the baseline versus the augmented. They are in the STM, you can look them up. And finally, there's to document any required science traits. If, for example, you want to put on a 10 kilogram, I don't know, cosmic ray detector and do astrophysics with it, you have to tell us why you need that 10 kilograms, and we haven't thought about it. Or you tell me that the Vizier mapper we're talking about is a silly thing to do. There's a better way to do the science for 2 kilograms less or for 10 kilograms more. Tell us that and make a suggestion. Remember, this is a study, it's not a proposal. So if you're willing to share those ideas with us, we would like to write them down and understand the state of the art. That being said, if you are still out there, which I think you are, we have just done the hardest part of the thing I think I've seen so far in this meeting is to walk through an STM with people. And I'm ready to hear input. And if you are on the Google Doc, I'd like to see you, feel free to go ahead and add to it. Thank you. If you want to unmute and would like to start discussion, feel free. Uh-oh, do I have crickets? Todd, I see you're out there. I'm going to actually ping you if you don't mind. Use you as a start. If you have an idea of how you would use ISP to do, and if folks don't know, Todd Lauer is the first author of a brand new paper that just actually got discussed on NPR about using New Horizons measurements of the optical background using the LoRa camera, the same one that took the beautiful pictures of Pluto and MU69 and mapped those surfaces, to try and to get a good, better estimate, a new estimate of the cosmic optical background. And that tells us about the galactic optical light and the extragalactic optical light in the first stars. So I'm going to I've just pinged Todd, I see he's unmuted. And so there's something, what we do with an ISP that could do better than New Horizons, that we could actually get to a cleaner, quieter part. of the sky. So go ahead, Todd, if you have any comments.
Yeah, I didn't know you were going to point the fickle finger of fate at me here.
You speak well, and you know you know a lot about these systems.
Right. First of all, I should say that I'm not part of the work that your group has done on ISP, and I know only a little bit of it from seeing the seminar that you gave, I guess, a couple weeks ago. And so what you're all trying to do is is something very different and quite ambitious, to look at multiple wavelengths over a very, very large area. The work that I have done is very, very modest, using LORRI on New Horizons. And so I think there's about 5 orders of magnitude between what we attempted and what ISP wants to do. So I'm not really sure I can say anything intelligent.
Okay. Maybe I can help you by riffing a little bit on what you've done. So,
well,
okay,
I guess, but just to finish though, I mean, what I would say is, I do notice that, you're going to have to spin this, and it's extremely challenging to eliminate sources, to recognize them, take them out, and so on and so forth. If I were to approach this myself, I would certainly go for a stable camera that could get deep imaging, is very well characterized, and not have to deconstruct something, caused by smearing stuff all over the place. So that's my own reaction, is I'd go for something, a bit different. I would, for example, if I were to try this, I would be interested in what the planetary component of ISP would be, and attempt to live off of that sort of camera. So I'm not really sure I can say much more beyond.
No, Todd, that was great, because we need to start off.
Approach.
And so Todd was using the planetary camera, if you will, on New Horizons, which, if you can see my cursor and see my screen, LORRI has a midpoint bandwidth of what, 0.7 microns wavelength?
A little bit to the blue of that, but yeah.
So about here, and Todd's new measurement is, I don't think it's this one. No, in Lauer et al. 2020 is not on here, but it's not inconsistent with, I believe, the current models. On the other hand, what I remember asking Todd more than once, that it would be really nice if we could also take some of the MVIC measurements that go into the very near infrared on New Horizons. But the answer he got was that camera had its own issues and problems that may be very challenging. So there's an example of where, if we had a purpose-built instrument, or we actually thought about adding that capability to a similar kind of camera for ISP, we could actually extend that kind of analysis down over here, where the tension seems to be very high between model and observation. And if you haven't read the new paper, Lauer et al. Is just out on the streets, and it's getting a lot of interest. So this is not just a pie in the sky cosmological question. This is something that apparently the public is interested in as well.
Casey, we have a question in the chat.
Please.
From Isaac Ashland, and he asks, how exactly would we determine the degree of reionization that occurred during the initial star and galaxy formation? That seems to be a particularly interesting question. And I guess to build upon that, if you look at the plot that you show, there's also the EBL from galaxies, looks to be about an order of magnitude above the signal from the reionization EBL. Is there sort of pragmatic ways in which those can be separated and analyzed?
That's a good question. Mike, are you on? I'm going to defer to an expert. I know enough to get.
Basically, you do this with color component separation. So you know that in aggregate, galaxies have a pretty smooth spectrum. And you know that early galaxies have a break in their spectrum having to do with Lyman alpha that gets redshifted into the near infrared. And so by knowing those things, and possibly some other tricks, you can basically decompose the populations that way. But this is fundamentally an aggregate measurement that you you're measuring integrals, and in order to place constraints on models, you have to take models and integrate them in suitable ways and compare to the measurements that you make. It's not a direct measurement in the way that like a Hubble deep field would be.
Thank you, Mike. Isaac, does that answer your question?
Yeah, I think so. It's just an idea I hadn't really thought about before, and it's really interesting. So,
yeah,
thank you.
Not a problem. This is a you know, I know that some of the people on the phone have to listen to this all the time, but some people maybe who are newer to it, this is a rich and deep field with its own history and ways of doing things, and we have a lot of tricks we can throw at this sort of thing.
Yes. Thank you.
Oh, those are good questions. And many of us on this call are planetary astronomers or heliospheric, and this is thinking of the universe as whole is a very different kind of world. I know this because I straddle the boundary. I started out in cosmology, and I have many friends who tell me that all I do in my career is study the local dust bunnies, comets and things. And to them, a galaxy is a point particle. It's a very different way of looking at the world than folks who study the local stuff. And one of the reasons I study the local stuff and think it's interesting and I'm excited about ISP is we can reach out and touch and visit the local stuff. I think all the science is good, but there's just very different ways of looking at things. The fact that there's crossover, it just tells you that there's information, these photons are out there and we can collect them. And I'm always go back to this, is that even when you look at this is the all sky as seen from the Earth, this black here is not that terribly black. That's what, in this scale, it's a lot darker than the galaxy or the Zodi, but it's still telling you that you're still got contamination from the local stuff. And I would love to see this sky map made from 100 AU out. That would be fantastic to see how much darker.
I have a quick question about that. This is Isaac again. How far would you have to go outside of the ecliptic to get that same kind of imaging rather than trying to go far away?
I mean, you're asking what is basically the scale height of the Zodi vertically rather than horizontally.
Yeah, and how hard would it be to get out of it that way rather than just?
It's a good question. I don't have the scale height on top of my head. There are people like Rowan Robinson and May have that. What I can tell you is I certainly remember the brightness of the Zodi when you look straight up, look at the ecliptic pole, is about a factor of 3 less than if you look in the plane. So you have to go figure out, it's also a cosecant theta effect, right? There's an air mass. You're looking straight up and it's a spherical volume. It's not, it's more like a football. Whereas in the plane, you're looking through a lot more dust. But I think also Andrew Pape has some models. If I had to guesstimate, unless Andrew's on, I would think you could probably go about a factor of 3 to 5 less distance, and you get things clearing up faster. So there is definitely, it's not a spherical distribution. It's squashed and more along the ecliptic plane because a lot of the sources, the asteroids, the Kuiper Belt objects, and the ecliptic comets are all relatively structured and bound around the ecliptic plane. Now, that all being said is that one of the things, I don't know if you were listening to the other sessions of ISP this week, it costs a huge amount of energy to go out of the plane. And,
yeah, for sure.
And the simple reason for that is that we're going around the sun right now at 29 kilometers per second, right? And the Earth is spinning 1,000 miles per hour. We have a lot of velocity invested, if you will, in the plane. So you have to boost from 0 to go out of the plane, and that's why it costs a lot. It's hard to do with a chemical rocket. It's a lot easier to use the velocity you already have and to stay in the plane. So I'm not disregarding your question. I'm just saying it might be logistically a lot harder to do. And even though you could get outside the Zodi faster, in the end, you wouldn't get that as far, and you'd go a lot slower.
And you probably re-enter depending on what exactly your trajectory was. You'd probably re-enter it anyway. Yeah, I was just a side question. I see someone else asked a question in the chat.
No, it's a very good question. I'll let you go. I just want to say one other thing that's very quick, is that one of the things we thought about on this mission for a while is if planet X, whatever you want to call it, if the object out there suggested by Brown and company is there, ISP may become a very different mission because it'll be the first to planet X and then go out.
Yeah.
Right, that's fine. That sounds very interesting until you realize that almost all of the arguments for where planet X would be is I think it's 30 or 40 degrees off the plane and about 600 AU out.
Hmm.
And,
And
in other words, then reality happens. I mean, I certainly would want to see in my lifetime somebody try to go there, but I'm not going to see that mission get there. And I don't think that we actually know how to get the C3 to get there with the current chemical rocket. Easily.
I don't know exactly how people are trying to figure out where this planet X is, but would it matter? Like, would you be able to see evidence of it even if it was at a different part of its orbit? Like if it, I'm saying, if it's on the opposite side from the bow shock and we're going towards the bow shock, would you still be able to get evidence that there's been a planet in that area?
It's a very good question. If you're trying to just see it by its optical brightness, it's far from the sun. It's actually very faint. However, if it is, I remember doing a simple calculation, if it is super Earth-sized or larger, it's actually going to still be very warm just from its condensation energy, not from sunlight. It's going to be very cold on 600 U, much colder than Pluto, just from the energy it absorbs from the sun. But the center of the Earth is about, if I remember, it's about 5,000, 6,000 degrees Kelvin. It's still hot from the gene's energy of just collecting, putting rocks together to make the Earth, plus all the radioactive decay. And there is heat escaping from the Earth and keeping us warm as well as the sunlight we get. So this object, if I recall, should be about 30, 40, 50 Kelvin just from its self-heating. And so you'd probably try to see it with thermal infrared eyes. And what you try to do, I suppose, is you put a infrared GoPro on an SLS and just launch on the biggest rocket you have, the tiniest mass, and maybe you could get out there.
But you'd want to know where it is, not just how far it is, right? I mean, like
right.
at that moment where in its orbit it is.
So hopefully Kirby's listening. This is a planetary question. I'm going to move us along a little bit. It's a fun thing to think about. We're talking about, and I've thought about it a little myself. We'll talk about it offline.
Yeah, we're just about out of time, and I want to make sure that we address one last question that's in the chat from Lizeth Gavelin. I have a question. Is the spectral change of dust at 100 microns related to the grain size distribution changing with the heliocentric distance?
The spectral change, meaning the predicted fluxes we expect to see in this plot?
Yes, she writes. And also, Elizabeth, if you want to unmute, feel free to speak directly to and ask questions to the group.
Yes,
but Casey, if you can address that.
I can. So you're exactly right, is that the total amount of light you see here is a convolution, is how many pieces of dust are out there and what temperature are they at, what are they radiating at. And if you remember, is from the plot I showed earlier, is that we think there are two localized populations of dust. There's this inner dust, and I happen to know, I can tell you, I could work it out from first principles. I happen to know from Kobe and getting the first SEDs on this, it's about 260 Kelvin because it's about 1 AU, 2 AU, and dominated by asteroids, inner asteroid dust. And that emits at about 8 to 10 microns. The second population of dust is coming from the Kuiper belt, and the temperatures out here are about a factor of 10 lower. So rather than a 10 micron peak, 300, one of the things you learn in infrared astronomy is 300 Kelvin is 10 micron peak. If you're going to 30 Kelvin, then you're going to be out at 100 microns. So what you're seeing here is, where is the dust and what temperature is that? And so there's a lot, and in fact, if you read Papel, Andrew Papel's paper that he wrote off of the Newton, and these two figures are from, sorry, I'm bouncing back and forth a lot, are from his paper. He argues that 97% of the dust mass, he gave us 2 sig figs, the vast majority of dust orbiting our sun is not here. We are swamped by it because we're surrounded by it and it's hot, so it dominates when you're inside it. But if you just count the total number of particles and total mass, most of it's in the Kuiper belt. Most of it is sitting out just like we see in other systems. And if that's the case, most of it being in the Kuiper belt, then there should be a lot of 100 micron radiation. And that's why you're seeing this dominate out here. So your question is right. There's lots of dust out there and a lot of cold dust. Then there is hot dust, warmer dust out here, but it's basically, you're outside of it by 5 to 10 AU. And you don't see much anymore. And that's why these are much steeper and why this is much shallower. It's a really good question. So as Mike said, these are integrals. You have to integrate all the emission from all the dust that's orbiting the sun. And what I just went through in maybe long-winded fashion is that the warm component, the warm part of the integral is mainly dominated by the inner asteroidal dust that's at 200, 300 Kelvin. And then you can get outside that pretty easily. And then the rest of the dust, and actually the bulk of the dust by number and mass, is out in the Kuiper belt, out to, this is a log plot, out to 50, 60 Kelvin. And as we said, we're still waiting. Here's a very strong prediction. It makes a lot of sense once you're outside the source region, and dust only spirals in as after it's created by grinding and sputtering. It's not going to spiral out. We should see this very strong drop off, and this is something we'll be very excited to see from the STC on New Horizons in the next decade. So I hope that answered your question. It's a very good one.
It did. Thank you. Yes.
Mm-hmm.
This is really exciting because it's like using the distribution of dust in the solar system as an analog to protoplanetary disk or planet formation.
Yes. And well, now, since I do debris disk for a living, I'll try not to go on too long. Our disk is rather sparse. If you look at, we often call our disk is one Zodi. By definition, we have one Zodi, one solar zodiacal cloud worth of dust mass and number. These guys you're all seeing here, these are probably hundreds to thousands of Zodis. I like to think of them, they're special, very strong cases. In this case, most likely you're seeing construction dust from forming a planet around a 10-year-old star. Some of the older ones, Beta Pic is 23. It formed a planet about 10 million years ago, but it's got a giant dust disk. Fomalhaut, we think is, that's a ring in a Kuiper belt, but we can go on for a while. But most of these guys are extraordinary, and you're seeing lots more dust than we have now. There are many arguments, and I think you might like this, that we have a very large number of planets in our system. Depending on who you talk to on a given week, we have somewhere between 8 and 10, and I'm not going to even touch that discussion. But the point is we have a lot in stable orbits, and those planets have helped to clean out our system and aggregated all the material in between them. We have a dynamically pretty cold system that is pretty well cleaned out compared to what you're seeing here. And so I've heard arguments saying it's one of the reasons we have so little dust in our disks, even though we do have it, is because we have got all these planets stably orbiting the sun and cleaning things out. Another way of putting that, if you go out any night and you look up, you're going to see 10 meteorites, 10 meteors every hour, and during a storm, 1,000 or 10,000. Those are pieces of dust that are aggregating onto our planet. The Earth is actually still sweeping up and cleaning out the solar system. Now, these other systems either are baby systems still forming their planet out of huge amounts of dust, or it's possible they don't have as many planets as we do. It's an interesting thing to think about.
And Casey, we're out of time for this talk. So to give everyone a couple minutes to stand up and walk around, we can pause here if that's okay with you, and pick up the discussion again in about 5 minutes on the dust discussion.
It is, and I would just exhort people, please, you're also going to see this in the dust discussion, please go to the Google Doc if you can. If you have a thought or three and you don't want to put it necessarily in this format, just type it in here. Please, we want your input. If you think, this is your mission too. If you think we're missing something, you want to see a piece of science, or you think we can do it better, please tell us now. Thank you. Thank you for your attention.
All right, thank you.
Take care.
Thanks, everyone. And the dust discussion will happen in this same Zoom room in about 5 minutes.
Mm-hmm. Thank you. Thank you, James. Did you stop recording?
Yeah, I can pause it for a moment and then restart it again.
Okay, thank you. So, okay. All right. Can everybody hear me and see my screen?
Yes.
Very good. All right. So I just went and gave a session, these are back-to-back sessions. I just talked about astrophysics. And now we're going to talk about dust science from the Interstellar probe mission. And we're going to talk about how you guys can help us, or the community, represented by this workshop audience, can help us improve our study. Because we need to turn the study in, we need to convince NASA and the world that this is the most important mission to be built next by the heliospheric scientists and community. Somebody needs to mute, please. And we need to do that as best possible. So what the most important thing to do is for me to show you what kind of dust science we can do from ISP, what we've thought through. And if you have any ideas on how we can better say that, or if we've missed something, we need to hear it from you. And I'm actually going to walk you through the Google Doc and parts of what we call the science traceability matrix. So, and I'll explain what that is in a few minutes. So first of all, this is not a solo project. It is myself and many other people. A lot of the people, there's overlap between our astrophysics and dust science teams. Mike Zemkov of RIT, Andrew Pape of Berkeley, Jamie Zaleh of Princeton, Mihai Haryani of Colorado, Bruce Drain of Princeton, Chaz Beichman of JPL, Viral Sterklin of University of Bern, Annie Chantal of Sorbonne, Rosine Lalamont of Paris, Jamie Bach of Caltech, and a bunch of APL leaders for the mission, Pontus and Ralph and Mike and Alice. So dust science, one of the triumphs, if you haven't been to previous workshops, is that the dust, what we call the IDA, or the Isp Dust Analyzer, is now part of the baseline threshold mission payload. And I want to make this sound like a congratulatory pat on the back. We, in previous workshops, managed to convince the heliophysicists that they didn't know about what could be a very important and possibly dominant component in a dusty plasma at their helios sheath and heliopause, and that they needed to go and take a dedicated dust analyzer to not only count dust, but actually measure composition through the heliopause and out in the nearby galaxy. And that is in the baseline payload, meaning this will, if ISP flies, this is going, a dust analyzer should fly as well. That's the current plan. So because of that, much science, like measuring in situ the circumsolar dust and the dust in the nearby galaxy, and its number and composition, can be done with this configuration, the baseline, what is now currently called the heliospheric payload. Now, other measurements like mapping the circumsolar dust cloud, its morphology, and comparing local galactic dust to distant galactic dust would require additional components. The planetary optical camera that is being proposed to map KBOs as we fly by them can also be repurposed or reworked to do other work. And as well as the Vizier mapper we were just talking about with astrophysics. They can do an awful lot to tell us about dust using remote sensing. I'm going to talk about this in summary slides, and we're going to go into this much more detail. I'll then list the workshop posters related to ISP dust science. I will also go into tell you about the items that are included in the current STM, Science Traceability Matrix. And as I was saying before, it took me a while to get to it. The Science Traceability Matrix is a document. It's kind of a grid. It's the way you start with science questions, like, assuming we're scientists on this call mostly. It's the way the scientists would say, this is what I need to go out and measure. This is the experiment I need to do with my spacecraft. But then how do I actually do my measurement, and what is the piece of hardware? What is the instrument that I need, and what kind of measurements, what kind of wavelengths, what kind of resolution, and what kind of pieces of dust can I accept? What kind of mass delta M am I going to be using? Those are the numbers need to be written in a hard place there. So the engineers can pick it up and say, okay, I need to go and actually design, buy, build an instrument that can do this. And if I can't do that with the current known technology for so many kilograms and so many watts, I need to go back to the scientists and say, I can't do this. Can you either modify your request, or should we stop doing it? And so this is actually how you go from experiment planning and theory to actually experiment reality and getting a spacecraft mission to do what you wanted to do, make your measurement. So this is critical for scientists to do. It's often rather hard. I find it not easy. And it's going to be interesting to do in a online community format, which is why we've got this Google Doc format. I'm going to go and talk for 30 minutes. And this is something very different. This isn't normally the way I do presentations, but then we're actually going to go walk through the Google Doc, and I'm going to inform you of the current dust science questions. And I'm going to ask for your input on how to make them better. We're going to suggest the suggested straw man payload, the current design for an IDA, which is, I believe I recall correctly, is a variation on a Europa Clipper instrument and SUDA. And we're going to talk about ops. What are the demands for dust science? Spinner or no spinner? My understanding is that, and this is one of the things the Helio folks liked, is that for dust science, we're happy if we spin slowly. And that's just at 1 RPM is a rough number that the Helio folks would be doing for most of the ISP's mission. And that's fine, because that means we cover the sky relatively well in all directions. Where do we want to get our measurements? Unlike the astrophysics, where data volumes are high, I think, and we're going to get to it, but I think the dust science data volume is actually quite moderate, and we want to get it throughout the entire mission. And we'll talk about that. Okay, so those folks who attended the astrophysics section are going to be staying for 2 shows, and it's always difficult. And you're going to see some slide overlap, because there is overlap between astrophysics, because there's astrophysical dust. So I apologize for that, but there's also some differences. And we need to talk about those differences. So primary goal, Ponte showed this on Monday, there's a lot of science that can be done as ISP flies out from the sun through the heliosphere out into the nearby galaxy. And I'll show that in the next slide. And there's all kinds of science. The primary goal is to study the particles and fields in the heliosphere, but we know that there are dust clouds right outside our door. We are pretty sure that we have some sort of shock, and that shock, while these are extreme examples, there should be a shock, and there could easily be dusty plasma out there in our shock. And nobody's ever actually taken a dust counter, let alone an analyzer, into that shock and figured out for humankind what the dust is doing there. And we need to go do that. There's an extremely low-hanging piece of fruit here, if you will. Just simply getting a dust analyzer. I say it in the Google Doc. Take a dust analyzer out past the orbit of Saturn and go to town and see what kind of science you can get. There's a huge amount of return. So this is pretty exciting to hear. And Frank, that's why I'm glad you're on, Dr. Cassini, dust. So the astrophysics community, there's all kinds of work can be done in looking at the cosmic backgrounds. For the dust science, the important thing to point out is that in the process of forming the first galaxies and stars, there was a huge amount of dust in the universe. And the infrared background, I'm not going to dwell on this because we're thinking, the infrared background, even from the first galaxies, the faint infrared is dominated by repurposed, the first light from the first stars and galaxies, absorbed and radiated by the very thick dust in those galaxies. So there's a lot of actually remote sensing dust science that can be done, not just in the local medium, not just in the galaxy, but actually in the background too. And of course, there's dust in the original dust disk that formed our planets and comets and asteroids. And so we're going to want to study that. We're going to be flying through the solar system's debris disks. So we're going to do tomography as we fly through them. We plan on turning around once we're outside of them and getting a family portrait. We want to compare what our debris disk looks like from the outside to other debris disks. It is also, I just learned in this meeting, we didn't see any evidence for dust around Pluto or in the environs of MU69. I don't recall the SDC on New Horizons. I say we because I'm part of the mission team, that we didn't see any uptick in the dust collection from the SDC. But if we go to a bigger KBO and it has no atmosphere like Pluto, it's very possible there could be some dust that's spalled off of that. And it's in bound orbits or even coming off of this day. We saw dust from OSIRIS-REx coming off an asteroid. Nobody expected that. If we could collect some of that dust, as Mihai has pointed out, and actually measure its composition, we might get an idea what the parent body's like. So that's an exciting idea too. We need to capture that into the STM. I think you all have seen this before. Pontus showed this on Monday. This is, if you will, the powers of 10. We start at the Earth, and we're going to fly out through the solar system. We're going to fly out through debris disks and dust. We're going to measure that dust. We're going to do exciting solar system planetary dust science. We're then going to get to the heliosheath and the heliopause, and we're going to be measuring the dust there. And then we're going to get out into the very nearby galaxy, and we're going to get our first clean samples of dust. And I'm going to go into this a lot more, but there is tension currently between the dust that has been measured here, which ISM dust coming in at high velocities from the inflow direction, roughly the RAM direction, the sun is going through the local interstellar medium, and remote sensing measurements of dust out here, promulgated by people like Bruce Drain et al. And there seems to be, my simple understanding, and I'm perfectly happy to hear corrections or amplifications, is that the only kinds of interstellar dust we are measuring here from Galileo, from Cassini, from stardust, is silicaceous rocky dust. These are small pieces of dust, 0.1 microns or so. We're not seeing the carbonaceous and metallic material dust that's expected also at roughly equal amounts. And is that due to charging of that and then funneling of that dust away by magnetic fields in the heliosheath and heliopause? Is it due to some sort of destruction mechanism as the dust comes in? You would think carbonaceous dust would probably be more robust than silicaceous, so that's a little surprising if it's really graphitic. But there's tension. We don't know the answer. And we can model the answer, we can argue the answer, people are, or we could just simply finally take an experiment out here and start sampling the dust we see out here and say, oh, it really is what the remote sensor said, and therefore something has to be subtracted from it. Or no, it surprisingly isn't what the remote sensor said. And we have to rethink about our models for the remote sensing. Okay, I am not going to go through the details of this. Poptis also showed this on Monday. What I basically want to say is this, that you see highlighted in red. There are some fantastic series of models. People have put a lot of thought. This is way above my pay grade as a dust scientist and planetary and local planet, exoplanet astronomer. But what I want to say is that my understanding is that these models are if we will, a competition between the pressure one gets from solar wind flowing out from the sun, the rammed velocity of the sun through the local magnetic field, and then the flow of material in the local magnetic field, local galactic environment, excuse me, flowing in and past the sun. So you can imagine different cases, as Parker did many years ago. You can imagine a case where the solar wind dominates, pressure dominates. So basically you have a bubble. You can imagine another case where what dominates is actually the interstellar flow and or the local magnetic field, in which case you can get either a croissant, or if it's really, you're moving very fast through the system, the local system, you can imagine even a cometary going almost a 1D or a cylindrical symmetry rather than spherical. And we do see these cases in looking at different interstellar, different astrospheres. So all these models, however, in my understanding, is they're all generated assuming just ions and neutrals and plasma. I do not think that they have allowed, because they don't know what the dust component at all, for a dusty plasma. And dusty plasma can behave very differently. Again, this can get above my pay grade. I just know that you can't just simply assume a plasma is gas plus dust when the dust starts getting to be 20, 30, 40% of the mass. It gets very different behavior. So this is one of the questions we need to help them answer. This is one of the reasons why the heliophysicists wanted to see an IDA on their spacecraft. Lots of other questions. The bow shock. What's happening in that bow shock? Is the dust coming in very quietly and gently? Or is it coming in and getting heated up? As we see other astrospheres, and we see their shocks with Spitzer, we've seen with Spitzer, in the infrared glowing. So how much energy is getting put into that dust? And that's one of the things that happens with dusty plasmas. You've got another conduit, another way of emitting and dumping radiation into dust, and then getting rid of it through infrared radiation. How much of an important part is that cooling playing? I want to point out that this is Pontus's slide. You'll notice that he wrote down determined density, temperature, ionization, state of gas and plasma, and then I put in and dust. So one of the things we dust scientists need to do is make sure that we get fair shrift, that we remind folks that the ISM may be, the gas to dust in the ISM may be 100 to 1, but there's still, dust can be very important. And so we need to remind them of that. And again, that's why we're flying. So I alluded to this. Here is the actual, some images. Here are astrospheres. These are not artist renditions. This is an artist rendition. These are real images of very bright stars with massive stellar winds and very and high velocities through their local relatively dense ISMs. But you're seeing very clearly evidence for shocks and for glowing thermal infrared radiation as well as UV scattering. And you notice that you can see, as I mentioned, you can see, here's your models of a spherical stellar wind dominated or of a magnetic field velocity dominated. And you see all kinds. This one is very spherical, most likely wind dominated. And this one, on the other hand, Myra, very different, is dominated by the ram velocity through the local material. So you can get all kinds of different schemes. We know that we're moving about 26 kilometers per second relative to the local ISM. So if I remember, I think Mary is moving upwards of 100 kilometers per second, so much higher speeds. So if I understand, and again, above my pay grade, kind of naively, my understanding is here's heliospheric models. This is mostly driven by the magnetic fields, not by the ram velocity. And our wind is relatively weak, unlike M-type star Lam-Ceph, which is dominated by the wind, which is a bubble. So most folks, if they were betting folks, would think this is the old cometary model, but then you have Mirov-Ofer's current models, which look more like a croissant. And having listened to some of the talks this week, I'm beginning to realize it's a lot like a ball, so a spherical, but with two kind of tails rather than a simple tail. So take that for the grain of salt and for as much as I can get in trouble here. So there's lots of discussion, there's lots of modern developments. These are old models. And what role does dust play in this? Now, I mentioned the disconnect about dust science. And this is where I know, again, enough to get in trouble. I'm going to introduce it. I'm happy to hear amplification of this. The blue line here would be Drain et al.'s model of what they expect from remote sensing for the dust. So carbonaceous silicates, expected density, and this is versus grain mass and, if you will, grain size. This is what Ulysses and Galileo, not Cassini, so only UGG, not Guck. And the Landgraf et al. Published in 2000, and you'll notice that there is a large disagreement between what was measured and what is predicted. Not only is there a dearth of very small particles in the measurements, there's also an excess of large particles. And then, as I mentioned, we did some research on the few ISM grains that actually have been collected and analyzed for composition in the lab, and mainly stardust. And they all seem to be silicaceous. So what's going on? And that's a very good question. We also believe from remote sensing that there is structure in the local clouds. There are some arguments that within a few thousand years, the sun is going to leave the local densification, actually go to a cleaned out region. So actually, I should point out it's heading this a ways. Here's the vector. It's going to head out this a ways. So it'll be very interesting to see if we can measure what we measure now, and will we precede the sun? Or can we actually get out faster to this rarefied region and learn more about the local density fluctuations? I mentioned very quickly that there is dust in the circumsolar disk, and there is dust to be learned. This is actually currently STM, it's in the planetary section. That's because when we were writing the STM, we didn't write it by heliospheric science versus dust science versus astrophysical science. We wrote it by helio versus planetary versus astro. So dust actually falls in a lot of different places. And that's why you're hearing it's a little bit of a polyglot. Dust can be coming, as I mentioned, from KBOs. It can be in our very early debris disk and what eventually got incorporated into the planets and asteroids and KBOs that we know and love today. It could also be around other stars that are much younger than ours, as I'm going to show you. Beta Pic is the nearest system we think made a planet within the last 10 million years. I can find my cursor. Oh, there it is. And you might notice that this looks a little bit warped, and that's not an artifact, that's real. We now know that the planet in here is tilted. And there's a second planet that has just been found in the last few months, by the way, Beta Pic C. And the reason why you're seeing some warping in this dust disk is that one of the planets is tilted versus this axis here. So that's pretty exciting. Of course, the famous Fomalhaut system, which is much different. These are all Kuiper belts you're looking at. This is because asteroid belts would be way down in here and hard to resolve. This is most likely a very thin ring of material that's been densified and could be slowly forming a planet very far out. One of the interesting things about debris disks is we noticed that systems with debris disks seem to have more planets. That doesn't sound too surprising, but we statistically have shown it. Our debris disk, on the other hand, is rather rarefied. We think it's maybe, we're 1 Zodi. The system I'm showing you here, Beta Pic is probably 10,000 Zodis. This is probably a few hundred Zodis. There's a lot more dust in these systems than us. They're a lot younger though too. So that's one thing. Here is a montage of stars seen from Hubble, all with beautiful circumstellar debris and planet-forming disks. And so we know disks happen. These are all Kuiper belts. Again, the asteroid belts would be within the occultation spots and hard to resolve versus the star. But we know they happen. And as I've actually taught my New Horizons team, hopefully, they were listening, is that we naively expect every system to have a Kuiper belt, every system to have an edge, because their original planet-forming disk stops somewhere. And so they should form, and Kuiper belts at the various farthest regions from the star, unless there's a binary companion, should be stable. Like the MU69 object that we passed by, it's a cold classical. It's just too far out from the planets and the sun to have been perturbed. It's been going very quietly in a circular orbit of 45 AU radius for 4.5 billion years. So a lot of these stars are most likely doing the same thing. Asteroid belts depend a lot on the planetary architecture inside, whether they're stable or not. And if you didn't know, a lot of our asteroid belt, well, we have asteroids in stable regions. We also have regions that Jupiter has repulsed and removed all the asteroids from, the new 2 and the new 6 resonances. So asteroid belts may be rare, and we don't see evidence for a lot of these disks with asteroidal material. We see a lot more icy ones. Okay, our own system, let's get back home. We have 2 debris disks, one formed by asteroids grinding and getting sputtered, and inner system Jupiter family comets that are subliming and cooking out dust and gas. Ones that are, those intersystem comets are typically in 2-to-1 resonance with Jupiter, have orbital periods 5, 6, 7 years. We also have an outer disk, which we have now just found with New Horizons. It's due to Kuiper belt objects grinding and sputtering. And we have given the brand new New Horizons results and one chord through this, Andrew Poppy et al. Have written a new paper showing you predicting what we think the debris disks combined look on the solar system look like. And Andrew did a wonderful piece of work with this. It's data driven, if you will. It still has one chord, so it has some, it would be nice to get a whole bunch of chords, or even better, go outside the disk and look back and take a picture, which is what we're gonna do with ISP. And one of the things that came out very quickly from his results, let me see if I have them here, I don't, is that he estimates that 97% of the mass in the solar system's debris disk is here. Only 3% is here, which is absolutely not what you would think if you look at the just the night sky and look at the brightness of the night sky. But we are dominated. The reason why is that this dust is about 300 Kelvin. This is about 30. So, and luminosity goes as T to the 4th. So one reason is that this dust is a lot hotter and brighter. The second is that we live inside this dust. And so it surrounds us and glows, and it's hard to see. And here's an example of that. We are living inside. This is the galaxy, very bright. Oop. And this is the dust and its thermal emission and its scattered light. If you look out after sunset in a very dark sky, this is what happens when you look in the ecliptic plane and you see that dust. It is very much dominating the night sky. So we know there's lots of dust out there, and this dust, now David Nussworny has argued very persuasively in a 2010 paper that more than 90% of the dust is coming from comets, not coming from asteroids. I show you the asteroids because they're easy to show, but the argument, the current understanding is that 90% of the Zodi dust, the warm dust I'm showing you here, is actually coming from comets subliming, and about 10% is coming from asteroids. Now that's of the 3% that we think now Poppy et al. Argued is it here, and 97% that's in the Kuiper belt. So how would we do any sort of measurements? Well, there's two different things you can do. I'm sorry that it seems to be getting cut off a little bit. It seems to be a conversion between different PowerPoint sets, slide sets. One of the things we would do is remote mapping. I just talked about this a lot in the astrophysics session, so I don't want to repeat myself too much. One thing would be take a 3 thermal shield nested, very simple 7 to 10 centimeter, I think he's got this older table, Mike Zemkov, 7 to 30 centimeter aperture instrument. Relatively simple optics. You have a beam splitter. You can split in far infrared and visible near infrared. You send the visible near infrared to a 0.5 to 15. I think we've extended this out. 0.5 to 15 micron R, about between 30 and 300 spectrometer. So we can do mapping spectroscopy. And then we have some big fat pixels at 30, 40, 60, and 100 microns that do just simple mapping of dust. The reason you do 2 different wavelengths, this will get you a lot of EBL signs, so cosmic background. It can also do what the Lisse spectrometer did on Pluto and MU69 at a planetary surface. And so you want to have good spectral imaging. You want to be able to tell what ices and rocks and things are on those bodies. The far infrared is going to be tuned and optimized. This is going to pick you up your colder Kuiper belt dust. This will get you your warmer asteroidal dust. And this is designed, these 30 to 100 micron big fat pixels are designed to pick up the faint but pervasive emission from dust in the Kuiper belt. So this is remote sensing. This is all based on a small sat designed by Mike Zemkov et al. Up at RIT. It's small and it's designed 4 or 5 kilograms. About 10 watts, if I remember, and depending on whether we're doing passive or active cooling. So it's very nice that there was already thought put into a design for a small sat that we could adopt to a mass and power limited ISP design. So this is a straw man payload. Remember, this is a study. This is not approved, or we're not saying you have to be this instrument, but this is an example of something that could fly at, and is at high TRL now. And so it's very nice to say that rather than nice dream, this is close to reality, and it's quite doable in a 2030 launch timeframe. So the second thing we would do, since I think most people on this call or this talk are most likely more dust collecting scientists, is we can improve on the student dust counter. that was flown on Stardust, Cassini, and New Horizons, where you've got capacitive, particle comes in, punches out a bit of capacitive material, creates an electrical pulse, and that's collected and measured and analyzed. And from the size of the pulse and the width, one can get an idea of the mass and velocity of the, basically what kind of hole did you poke in your dielectric. And so this is classical, it's wonderful, and did a very good job. It did the work I mentioned on New Horizons and actually detecting the Kuiper Belt dust for the first time, but it doesn't tell you chemistry. It doesn't tell you what is that dust made of. And so one of the great arguments currently going on is, what is the dust in that Kuiper Belt, the dominant dust in our debris disk? Is it rocky? Is it icy? It doesn't seem to be very easy to detect thermally. It doesn't seem to be very bright optically, so not very shiny. So you'd probably naively say it's probably small and dark, but we don't know for sure. And we can argue back and forth a lot, or we could actually fly a dust composition analyzer, which can get you count rates and also get you compositions. And we can take it through the Kuiper Belt and out into the nearby galaxy and do all that fantastic science. And I probably don't have to persuade anybody on this call we need to do that. And the nice thing about it is that Mihai and Jamie and Sasha and company have shown us that if you take a pseudo kind of design, what's been currently designed for Europa Clipper, and you throw away the shielding, which you don't need because we're not going to be in close Saturn proximity and a high radiation dosage, you can actually get your masses down, my cursor, down to 5 to 10 kilograms. You can get TRL is relatively high. You can get reasonable collection areas and count rates. I'm going to show you this in a second. And you can do a lot of very, very interesting dust science.
Casey, we have a question on that slide from
Sure.
Burley Durkin. Is there a possibility to measure composition of grains larger than 300 nanometers?
Jamie, you on? I think the answer is yes.
Yes, I'm on. Bill, absolutely. It's just a matter of if we can detect those impacts based on their impact speed. So the larger the grain, the better we can do with the composition, but the less impacts we'll get.
I hope that answered your question, bro.
Yeah, what is the maximum size that you can measure for the composition?
I don't know exactly, but I think it's more of a matter of the impact flux. At a certain point, you're just not going to get hits above a certain size. I think that will be the driver, not electronics. But if we're comparing between Interstellar and Kuiper Belt, the speed and mass do play into where we set our threshold. So I can't give you a definitive answer, but hopefully that's helpful.
And I think most folks on the call know that the ISM dust should be very small, submicron. And the planetary dust should be large.
Can I add to that?
Sure, yes, please.
I mean, there is kind of an upper limit. You can oversaturate this kind of detector in ions, but it's certainly above 300 nanometer. It's a matter of design, actually. So, but something like a micron should be not a big deal at the expected speeds.
I actually want you, so remember, I'm going to take you through the STM and the slightly painful document that we all need to work on. And I actually want to capture numbers like that. That's actually what you're suggesting is what is the mass or what is the particle size range that we should be accommodating. And I'd like your input on that for the STM. So good, this is good discussion. This is exactly what I'm trying to promulgate. I can't tell how many people are out there and whether this is all background and they know everything here. So, but let me go on a little bit and then we'll get to that document, more discussion. The interstellar probe, we realized that you don't just need to measure, of course we're going to have an IDA, we're going to expose it to the dust, we're going to collect dust counts and get chemistry compositions as we move out. But we can also do other things. We don't just have to wait until we go out beyond the dust cloud, turn around and take this beautiful picture of the sun surrounded by dust cloud, which is fantastic, by the way, and I would love to have it. But we also realized that we can do what we call tomography. The same way that if you were walking through a fog bank, and as you come in towards the edge of the fog bank, when things become optically thin and you start clearing out, you realize that you're near the edge of the fog bank and you're getting some idea of the structure. You can do the same thing for the solar system dust cloud. We can actually stare, the easiest way to think of it is stare just straight forward on the RAM direction. And we can constantly take pictures every month, every week, every month or so. And we can look and see how bright is that background. And the background should be going down and down and down and then boom, way down. And once we get outside the cloud. So that's an example. It's very, very simple hand waving, but that's what tomography will do. If we can actually take pictures of the background and then invert them to figure out what was the cloud structure and 3D density. Another way to put it is what was the integral of dust in the line of sight in front of us. For the simple example I showed you, you can actually invert that and get the cloud density. I don't think I have the slide to show you, but it's actually the same physics, or excuse me, mathematics. It's called the radon transform that people use when you go and get a CAT scan with X-rays. You actually get a whole bunch of different lines of sight through a body. You project the absorption, in this case of X-rays, onto a two-dimensional plane, and you invert that to figure out what was the absorber, what was the three-dimensional structure of the absorber that those X-rays were traveling through. Our problem is slightly different, but it turns out it's the same mathematics. We're trying to figure out what is the amount of light coming from a three-dimensional structure as we're traveling through it. So it's known science, and we've actually started applying that. There are some limitations because there are some non-uniquenesses. You have to be careful with the radon transform. And that's one of the reasons why it'd be fantastic if it's tomography, but then you want to get ground truth and turn around and take a picture that looks hopefully something like Papi et al.'s model and see whether that was exactly what we saw, what we actually figured out from the tomography. Now, I will say there's some slightly self-servingness here. I did some simple math that's kind of morbid. I'm 59 in December, and we're going to launch in 2030. Let's just face it, we're not getting to 50 AU probably in my lifetime. But you kids on the call. So I would like to do tomography now. You'll get the look back image. Don't worry, I'm not that morbid. I'm laughing because one of the things we're realizing also, if you've heard earlier talks, is this is going to be a generational mission spanning 50 years. So maybe some of us older people are going to launch it and you kids are going to finish it up, and it's still going to be exciting. So hopefully this is exciting in and of itself. We'll get the shape of the cloud from remote sensing. And of course, here's showing you what New Horizons did. This is from Papi et al.'s 2019 paper. Here's the arc, or here's the chord that New Horizons took through the solar system. Here, I had to explain this to the astrophysicists. You guys will get this really fast. Here is the contribution from the inner dust, from the asteroid belt, and from the short period comets. See how fast this is a log plot. See how fast it's coming down. The fact that it plateaus, that it doesn't just go to zero by between 5 and 10 AU outside the asteroid belt, outside Jupiter's resonant comets, tells you there had to be another source. And the fact is it's plateauing. That other source is the Kuiper belt dust. And so New Horizons pretty much did the ground truth, actually measured and detected the Kuiper belt dust, part of our debris disk for the first time. That's very exciting. What I'm also going to be excited, and I will be around for this, thank you very much, is I want to see when New Horizons goes out here. I want to see once you get outside the source region, the second source region, you should see the dust counts in the SDC drop off drastically. And this is Andrew's model, and we'll see. And I think we're at 50 AU now, right? If I recall. So I don't know if I've seen the latest numbers here. We should start seeing a drop off. The error bars are large, so you probably need to get out to 60. But that's going to happen in the next few years. New Horizons is moving about 3 AU a year. So these are impact rate estimates. These are a little bit older. These are Jamie's slides, I think, from a year or two ago. And this is just to say, Jamie, do you remember if you don't mind unmuting, you remember the aperture you assumed here? He's giving you a count rate for, I think, if I had to remember, 10 centimeter aperture?
I don't remember. I think that's per area. So I don't think we assumed an aperture for that one.
But one of the things that Jamie found is that we can get a reasonable count rate given the pseudo design. That one of the trades that we're going to be encountering is the bigger you build the aperture, the more massive you are, but the better your count rate. So mass is critical on this mission because more mass means you're going to go slower. So there's going to be an optimization point. The powers that be would probably like to drive us down to zero mass, but still make counts. Of course, we're going to want to have large as possible. Somewhere in between is a sweet spot. Did I say that okay, Jamie?
Yeah, that's great.
All right, so there's some trades, and then Jamie's already been asked what he thought was a reasonable size aperture. And we can talk about that a little more once we get to the Google Doc. So it's just giving you a whirlwind tour. I wasn't trying to give you an expert tour because I wanted to introduce the problem because we need to get to the STM. But what I want to conclude is I see very simply, it isn't very hard to say or show, is that an ISP dust analyzer just out past the orbit of Saturn will give you composition in the Kuiper belt dust. It will hopefully reproduce or enhance a drop-off measurement. It's going to tell you about dust in the heliosphere and the heliopause and the heliosheath and what's going on in the bow shock. And then it's going to get you out in the nearby galaxy, and it's going to test this question of, is the dust really what Drain et al. Argue it is, or is it like what Cassini Cassini, Galileo, and Guck and Ulysses have measured, and for some reason we don't understand. I, being somebody who does remote sensing measurements of dust and debris disks and done it for a long time, I don't understand, and I also am going to be careful here because I'm also an observer. Models are nice, but observations and measurements are better. It's hard to understand how this model could be wildly wrong. It's also hard to understand how they can be so different. And that's why I kind of favor, if you will, the idea that there is some shielding and defocusing and removal of the carbon, but that's absolutely not proven. All we know are the real life measurements, and they've been carefully checked by more than one instrument suite. And we have to go out and kick the tires. You go measure. And so I see this as a fantastic hotbed, fantastic source of incredible dust science in so many different ways. And just the IDA itself. And then, as I mentioned earlier, if we also put on the remote sensor, combine them, and you can even go out farther in the galaxy and make comparisons. Okay, I think we'll just go past that. So this is kind of said in, if you will, in Pontus showed this on Monday. Here's our local, here's what people see on Earth. Here we have our Zodi cloud. We're going to get outside the solar system. We're going to look at the local dust clouds. With remote sensing, we're actually going to be able, if we have 0.5 to 15 micron spectrometer, and we have some big fat but very useful long wavelength, we're actually going to be able to see through the galaxy and measure dust in other parts of the galaxy. And then, as I mentioned earlier, if you want to talk to the astrophysicists, they'll show you that the cosmic infrared background is dominated by the very first galaxies and things you see in mega clusters and at very high redshifts. So there's dust there too. There's a lot of science we can do in dust. Okay, that all being said, clap, 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 clap. Thank you for your attention. Now on to the work. All right. So first thing is to list the workshop posters related to ISP dust science. And this was just simply my going to the webpage and going to the posters and saying, clicking the radio button that said dust. And this is what was returned. So I want to advertise all of these because some of the people are probably on this call, or on this Zoom call, as well as if you haven't seen them, I think you might be very interested in reading them. So everything from a long-term study of interplanetary dust impacts by Voyager 1, by Janes et al., peculiarities of the interstellar dust distribution in the heliosphere, Godenka et al., elemental abundances in the gas and dust in the local interstellar clouds, Slavin, Interstellar Probe, a golden opportunity for in situ interstellar dust research by Sturken et al., infrared mapping of PAHs in the ISM, and I'm assuming everybody knows what a polyaromatic hydrocarbon is. If you don't, think mothballs and think fused benzene rings. And these I think of them as a molecule since I'm a chemist, but there are many people who think of the larger PAHs as very small dust particles. They're kind of an intermediate. They can be anywhere from carbons, 12 carbons up to hundreds of carbons. So they kind of straddle the very large molecule, very small piece of dust and cluster kind of regime. But Caitlin Ahrens has pointed out that there's very interesting science. And this comes with astrophysical eyes. One of the things you do when you look at other galaxies is you see that they light up in PAHs. The PAHs are very, very good at fluorescing. They absorb UV light and they re-radiate in the infrared. And this is one of the major sources of infrared, other than dust and thermal continuum, in the universe. So we want to know what the PAHs are locally. So that is very interesting. And if we actually go out and measure them with the IDA, with the neutral gas spectrometer. Again, remember these things fall in between. It would be very interesting to see what kind of PAHs and how much of them are out there in the galaxy, nearby galaxy. I'm going to go through these other ones. These are more, the reason they're blue is they're not directly dust related, but they are because they relate to what is the helios sheath and heliopause structure. And these are all probably assuming that there's no dust there. And so they're secondary in one way, but they're primary in another, in that if I'm talking to a dusty audience, we could help possibly rewrite the models and the understanding of what's going on with the heliopause, because we're going to force people to think about dusty plasmas. And one thing to point out simply is that because there's no understanding of the amount of dust in the heliopause, nobody includes it in their models because it's an unconstrained parameter. So if we, even a simple constraint, if we get a dust density at the heliopause within a factor of 2, that's probably a huge advance for understanding, doing the modeling there and what's going on at the heliopause. All right, instruments for dust science. You've heard me talk about this. I'll just go quick. IDA, I think everybody has seen that and would like to see that fly, and we have a basic understanding. SUDA light, if you will. And the remote distant large scale dust mapping, I mentioned you can do that with measurements with a Visier spectral mapper, with an optical flyby camera, and even with a UV imaging spectrometer. Any way you can collect photons that interact with dust. I mentioned this earlier, the operational requirements, as far as I can tell, another reason besides all this interesting science and how dust affects the heliopause is the heliospheric scientists heard that for dust collection, the IDA is happy with a spinner. There's no problem. And the question is, what's too fast or too slow? I think the current numbers are thinking is about 1 RPM after they put the booms out on ISP, and I think that is fine. If anybody wants to hold their hand up and say that's not fine, I would like to hear it now or later when we get to the STM. Roughly, we want a small cone angle versus the ram direction. My understanding from Jamie is it's a two-pronged optimization problem. You'd like to be right in the ram direction to get the highest velocity for your dust and get the best ionization, but you also want to be able to cover the sky, so you don't want to be perfectly in the ram direction. You actually want to map things out. So you want a moderately small cone angle versus the ram direction. And you'd also like to go out, the direction of the spacecraft, you'd like to go out the direction the ISM dust is coming in. Right now, the current, I should have written this down, I didn't in the slide, I haven't. The current nominal mission is going to take us 45 degrees off the heliospheric nose, the direction in which the sun is moving through the locum. And that's in order to do the best job of discerning between the different kinds of models, cometary versus sphere. And very simple in hand waving, just to point out, if you, in your mind's eye, you take a sphere and then you say, okay, it's not a sphere, it's a comet, right at the nose, they're going to look roughly the same. They're going to have roughly the same curvature, and you're not going to be able to distinguish those two models. But if you take a sphere, and again, you take this kind of cylindrical comet hot dog shaped thing, and you put it together in your mind's eye, you can imagine if you go out sideways or kind of sideways, you're going to be able to tell really fast if you're a sphere or not. So that's where the largest lever arm, if you will, between the different heliospheric, the three-dimensional models of what's going on at the heliopause. And that's why they don't want to go straight down the ram direction. And we have to piggyback on them to a degree, a lot of degree. The distance to the observations, we want, in my understanding is dust science, you're going to do all the way from the Earth all the way out until the ISP is not talking to us anymore. And let's not think that. Just keep measuring dust. And the only difference in the dust is that the dust rates are kind of be highest right near the Earth and in the asteroid belt. They'll fall off as you get to the Kuiper belt not because there's less dust, but just because it's the larger volume. And then you're going to want to measure them through the heliosheath and the heliopause and out in the galaxy. So we want this on 24/7 if we can get it. The data volume should be relatively low. It's like the return for when a particle experiment measures a particle's charge and energy and velocity in a magnetic field. It's not like you're producing images. So data volume shouldn't be a big problem.
And Casey, we have a comment on the previous slide from William Kurth.
Yes, please.
While not a dust instrument per se, the radio and plasma wave instrument can do a good job of obtaining dust fluxes, very complementary to a dedicated dust instrument.
Again, in fact, that's been demonstrated on, for example, the Dawn mission. What you do is you count on a dust particle coming in and hitting your spacecraft and creating little plasma clouds. And for example, the ISM dust is coming at 26 kilometers per second. It takes about 8, 9, 10 kilometers per second to vaporize rock in an impact. I happen to know that from lots of other work. So there's plenty of energy in these dust particles to come in and to actually vaporize themselves and a little bit of spacecraft. Don't worry, our spacecraft's gonna be fine. These are really tiny craters. But when it vaporizes, it's actually gonna ionize and it's gonna create a little plasma cloud that can get picked up by the plasma and detectors. And the radio, it also, if there's an acceleration of the charge in the plasma, it's gonna create a little electrical pulse, a radio pulse. And so this has been demonstrated on a number of spacecraft. So thank you for pointing it out. I'm going to give you a little homework assignment we're about to see. Can you write that down in the Google Doc we're about to go to? Please. Thank you for reminding me of that. It's obviously something we've missed, and you've just paid for this meeting and this discussion.
And the Google Doc link is in the chat.
Yeah, we're about to go to that. Okay, so thank you, very good timing. And I did not pay him to bring that up.
Hey, Casey,
Yes, sir.
when you get to the Google Doc, could I jump in with a comment real quick?
Absolutely. So for those folks who haven't heard my last discussion, the goal of this workshop is a little different than a simple science talk. And it's to familiarize the workshop community, that is you, the listeners, with current science engineering plans in the science traceability matrix and collect ideas for improvement. The science traceability matrix is how scientists talk to engineers. It's how we get our instrument. I think I went into this in some detail. And so we need to go, and I'll show you how it's built and what its current structure is. So I'm going to hold your hand and I'm going to ask for your input. And what we need from you, and we apologize for this, working on an STM is not easy even when we're all in a room together, because people have different ideas. It's kind of subtle, the language you want to put in there. You have a sentence or two to try and get everything done. And then you have a listing of instrument capabilities. The best option we have during these COVID times is because we're doing remote meeting format, is to pick things up and put it in a Google document, because we can get your input. If we all try to talk together in 25 minutes we have left, there is no way we're going to talk of each other. There'll be Zoom collisions, things just aren't going to work. So we can have one speaker at a time, like Mike is going to talk. But if you guys can think about what you're saying, if you can queue up to speak, but also if you can write down, if you have an idea in this Google Doc, it's really easy to do because we're going to take you there. Just write it down. We're not looking for really fancy statements that are going to, convince NASA tomorrow to fly this mission with an IDA. What we're looking for is creative input. What have we missed? Like we just heard, the radioplasma. It's a great idea. Or what have we misstated? You must work within current mission design bounds. You're not allowed to put in a 1,000-kilogram teleporter. That's not going to happen. We need something that's going to launch in 2030. We need roughly an IDA-like idea. If you have something better than the IDA or slightly different that can do the same science, that's fine. We don't need you to wordsmith. Even if you misspell things a little, I'll clean it up. We really want your input. And again, what have we missed or misstated? Don't bother editing other people's work. Just put your stuff in. We'll clean it up. And I also want to point out, this is a living document. The inputs are going to be taken for weeks after this meeting. So if you think of something tomorrow or the next day, and you have the time, please give us this input. And I would say, especially for you, the younger people on this call, you are the future, and this mission is a lot for you. And so it's going to be very exciting we need your input now. Don't be shy. All right, so I'm going to go take you to the Google document now. Hopefully that will work. And then we're going to let Mike talk.
Yeah, Casey, well, while you bring that up, do you want to let Michael go and we can double check that everything's pulled up correctly?
Yes, we can. So this is the document. One more minute of introduction and we're done. Then I'll let Mike talk. This is the document I'm about to take you to. Okay, you have the link. I'd like you to go there right now if you can. And this is the document. It's called Interstellar Probe Dust Science. I must admit, I found when I was editing this morning, I put a lot of what is in this document you just heard. So there's going to be some repetition, but the point is that you don't need to go and find that talk again. You just need to go here and you can go ahead and clean things up. And for example, you need to put in a space there. And I've also been a little humorous saying, take humankind's first dust chemical analyzer, this is the colloquial name for this document, out past the orbit of Saturn and kick butt. Think of all the cool science we can do. And if you'd like to clean that title up, you can too. You just saw all of this. Mike is going to talk, and then I'm going to introduce you to the actual details. We're going to walk through these questions. And while that might sound a little painful, it's going to be useful for us to do it together and for me to familiarize with you, to realize that we're doing it in a certain style, but we're also human beings, and this is where we may have missed something, or can be said better. And we're going to talk about the dust that is in the solar system. We're then going to talk about the dust that is in astrophysics and the overlapping. And we're going to talk about Helio has some questions about the dust that's in the local interstellar medium. They're also overlapping. So we're kind of polyglot, and we're going to show up in 3 different places. So with that being said, Mike, go ahead, and then we'll start walking through the STM.
Thanks. I think I'm going to address my comments to Pontus, but I think I'm actually talking to everybody. And Pontus, you're just the messenger, so you get the brunt of it. In the activity of thinking through these STMs as we were developing it, and then what you're going to see now and what everybody's going to be editing, there's been a overarching sort of architectural structure or assumption or something that roughly follows NASA's divisional structure, namely helio, planetary, astro. And I think the thing that's kind of come to light as we've engaged with this, at least for me and I think some others, is that those silos don't make much sense. In fact, ISP is really cross-cutting. And I know you know all that. Everybody here knows that. You can see it, and it's coming up in the chat and so on and so forth. And Casey's been saying it. But I do think we should maybe be getting away from phrasing things in that way anymore. We should really think about things. What are science questions ISP can answer, and what are questions it can't answer, or we can't afford the instrument, or whatever it ends up being. Because I think a lot of things are doing more than one thing here, and we're doing ourselves a disservice to be putting things into these artificial silos that NASA made up, 70 years ago for reasons that I don't know. Anyway, I just wanted to say that as a framing, a sort of architectural thought.
So, Mike, I don't know if Pontus has the opportunity to actually weigh in on this. I think he's double-hatted with a flight instrument PDR right now, even though you can see him.
Okay, fair enough.
And I'm
But
going to wait. Okay, go ahead.
I can tell you a little bit about this. We've talked to a number of very senior people in the community to try to tackle this issue, and essentially the conclusion we've come to is that while you are correct, and while science has no knowledge whatsoever of bureaucracies, that's probably a reality that we can help to shape through this mission, but it's not something that we're going to be able to combat as we begin this mission. And you have to look at the fact that the decadal surveys and the work of the national academies is directed by law, and that it feeds into future budgets at NASA, and to identify programs at NASA that have broken away, if you will, from that sort of internal structure in the Science Mission Directorate, would be to take this mission, which can be executed for a budget we believe that is not too far off of what Parker Solar Probe's budget is, minus Phase E, because Phase E is so long, adjusted for inflation, of course. We would take this mission, which looks like a good, strong, strategic, large, but not out of control mission like Parker, right? Parker's a well-controlled, cost-wise mission, and instead lump it into a program control office the way that Webb or now Mars 2020 has been. And those missions, from a cost control and a strategic perspective, they're in a different class than Parker, frankly. They look different, they feel very different, and strategically, I don't know that that's a healthy thing for this mission. And
No,
so,
I agree with that, and I'm sensitive to that too, having tried to do things like this in the past. But I think that if we can, it's this thing, right? If we can tweak the language a little bit, maybe we can be the change we're looking for. You know what I mean?
that's okay. So that's what I liked about your suggestion is you weren't asking us to grab a jousting pole and tilt at the windmill of NASA headquarters. You're telling us, and I did hear this, but I wanted to put that strategic landscape out in front of everybody as we talked about this. You're basically telling us that if we choose our words carefully, we can accurately describe all of the science, all of the strategic growth that we want to realize through this, and not use words that are co-aligned with the bureaucracy, because they don't have to be. There is a risk, and the risk is that we do it in a way that the folks who really matter at NASA headquarters, who are really interested in the success of this, might find it hard to recognize that what we're doing is relevant to their requirements and their goals and their priorities. And so if we don't use language that they're using to reflect the things that are very valuable to them, then we may lose their attention in ways that isn't helpful to us. And so it's a challenge, it's a balance.
No, it's definitely incumbent upon us to communicate properly to those people, because that's absolutely right. And anyway, I'll shut up now. But
No, this is important, and actually, I'm not surprised that this comment comes up in this particular session, actually, because I've learned from you and the others and Casey about what dust in and around our star means, its origin, what it means, what it grows into over the evolution of a star system. It itself is cross-cutting. I mean, we're talking about instrumentation that can, like, maybe characterize some of the dust created as it goes through the range of the asteroid belt, and then the Jupiter Trojans, and then the Kuiper belt, and then out in the interstellar medium. They all come from different places, and they all mean different things, and they're all important to realize. None of them fits clearly right into one bucket.
Yep.
It is planetary and heliophysics and astrophysics. So, yeah.
And this is, I'm going to chime in 2 cents and move us along a little bit.
Okay.
One is I'm going to agree and disagree with Mike. And before I do that, I'm going to say to the group, you may not know, Mike helped lead the effort that the Dust and Astrophysics team put together over a course of a bunch of weeks in September, October, and got the astrophysics and dust questions to the mature level they are in the STM today. So he's been thinking about this a lot, and he actually has a lot of credit, if you will, because he's done that. And so he helped put the structure and helped us get together and think. So that's why we're in the state we're in, which is we think is pretty good, but not perfect. So he has a right to ask this question, I think. Now, we want to be careful that we don't get into a high-level philosophical discussion, which I'm steering you away from that. But I also had the problem when I was putting together what you're about to see in the STM. I had to extract from 3 different parts of the STM because the dust questions were spread all over that, and that's why it's going to look a little bit haphazard. You have to pick something. I'm a slightly different answer than what Michael just gave you, is that you got to pick some way of classifying things. And if that is hurting our dust science, then we should push back. If it is not, we should just go with the flow we have, and this is a study, not a proposal.
So with that, Casey, we have 15 minutes until the poster session starts. Do you want to jump into that?
Let's move this along. I want to ask 2 things. I'm going to get to the STM and walk you through the questions. The other is I have asked William Kurth, he came up with a very nice question. I want him hopefully to chime in before we're done about whether we could use the radio plasma bursts. Could we actually use them as a primary dust counter? And Jamie, feel free to go, oh my God, no. And could it help us use that as the primary counter, whereas we could optimize the IDA for chemical analysis? We actually, right now, we're going to have the IDA do everything. Can we use the idea of radio bursts from impacts to our advantage? And, or do we just want to use it as a secondary dust detector and have those counts corroborate what we're seeing with the IDA? I just want to throw that out.
I think that's exactly what I was suggesting, was that the wave instrument basically uses the whole spacecraft as a detector. Mm-hmm. So the fluxes that you can detect with the wave instrument are probably larger than you can with any dedicated dust instrument. On the other hand, the wave instrument can't sort out the difference between mass and velocity. For example, we typically can't tell which direction the dust is coming from, although I think there's been some effort to do that on stereo. But it's fairly easy to basically run waveforms through a peak detector and look for signatures of dust impacts and just keep statistics. And so we can, hello?
Okay, so let me walk you through the STM real fast, and that's very interesting. I'm actually really like the idea, but I'm also leery about, you don't know whether your dust just hit a piece of mylar on your spacecraft or hit a bus, an aluminum bus, and so you're going to get different signals from different impacts. But with enough impacts, you should be able to figure that out. Okay, that all being said, is William, you and I, we need all talk, and I'm hopefully you can put some of this information in the STM I'm about to talk about. Okay, here are the questions.
Can I jump in just very quickly?
You're the boss.
No, not really. But so I'm literally listening in one ear. I'm in a review on the other. So when it comes to that cross-divisional science questions, maybe I misunderstood you, but I think you have the right thing going for you, or for us. When we speak about dust in the heliophysics goal, we speak about dust in the astrophysics goal, and we speak about dust in the planetary goals. Those are sort of 3 different sides of the same coin, if you will. We got to maintain that in the science traceability matrix. Science. That's what it is.
So Pontus is coming from the point of view, and Pontus, I'm going to cut you off and get moving. Pontus is pointing out because the dust sign is so rich, it shows up all over the STM. Therefore, it's really important to do. To summarize, okay. And I like where you're coming from, Pontus. It's a different spin, and it's actually important to think about. Okay, first question. These are the planetary sign dust questions.
Casey, are you intending to be presenting right now? On the,
yes.
So we cannot see your screen.
Sorry. I apologize, I'm rushing a little bit. Can you see it now?
Yes, we can see it now.
Determine the size, structure, composition, and dynamics of the interplanetary dust clouds throughout the solar system. So ask what is the mass contained in the inner outer dust clouds, just as I mentioned, asteroidal versus Kuiper belt, and asteroidal/cometary. What is the size distribution of interplanetary dust grains, and how do these constrain dust grain production mechanisms? For example, cometary shedding, parent body collisions, ISM dust, sputtering KBOs, etc. What are the dominant compositions of interplanetary dust grains, and how do these vary as a function of heliocentric distance? I.e., do you see a difference between asteroidal rocky dust in the very inner system and short period, well baked out comet dust versus possibly much more icy KBO dust in the outer system? How do ISM dust grains differ from interplanetary dust grains compositionally, and what does this tell us about solar nebula dust chemical processing? In other words, we've been basing all our understanding of ISM dust grains possibly from what we know dust in the solar system. What if there's a maverick component that we've just never thought about? We don't think there's anything crazy because we've done lab studies and we matched our spectra and all that good stuff. But what if there's something we just don't know, and you won't know, just like oxygen in comets. You don't know until Rosetta actually got to 67P to find it. Is there structure in the zodiacal dust cloud due to dynamical processes associated with solar activity, sorry. Comets, planets, asteroids, Kuiper belt objects, as these things, if a comet comes and breaks up, if SW1 turns from a centaur into a comet, we expect a huge amount of fragmentation and a dust outburst. We've seen asteroid-asteroid collisions with Hubble. Are these all creating little temporary dust clots? Was the collision that formed the Haumea KBO collisional family, did that create a lot of dust? We actually talk about that in POP 8 out 2019. Are there structures, processes in the sun circumsolar debris disk due to solar system formation evolution that we can still see today? Can we see the fact when Neptune migrated out? Can we see how it's actually entrained and sculpted the debris disk? That would be fascinating to see. And we won't know that until we go out with far infrared, mid-infrared, far infrared eyes and carefully look at the structure of the Zodi cloud, the outer Zodi cloud. All right, moving right along. Astrophysics, dust shows up again. What are the properties of dust in the ISM as traced by reflected starlight, and what they tell us about the dust origin evolution? Separate question. Now go use thermal infrared emission to do the same. We broke these two up because you're only allowed one question per box and because they're actually different measurements. If you look in the rightmost boxes here, the reflected starlight will be an optical measurement, whereas the thermal emission will be much longer wavelength infrared measurement. What are the properties of ISM PAWs? What are they telling us? While PAWs can be very, very strong re-emitters of infrared radiation, I know I have argued in the past that PAWs are not the dominant carbon source, if you will, or population of carbon-bearing species in the galaxy. I might be wrong. We actually think there's a lot of amorphous carbon, little, not graphitic, but amorphous carbon grains out there, glassy carbon. But that could be wrong because we know the PAWs are out there. So one of the things to do is go out and start measuring PAWs and carbonaceous particles. We can't measure the ISM carbonaceous particles in the system as far as we can tell. We don't see them in stardust. So what's going on with those? We won't know until we actually get a dust analyzer out in the galaxy. Here, this kind of related. It's the very local ISM material characteristic of ISM in the galaxy as a whole. Well, we're going to take our ID out as far as we can go, which is the very nearby galaxy, but we can't take it to the other side of the galaxy, not in anybody's lifetime in this talk. But what we can do is use the remote sensing capability to bootstrap. Once we're in the local galaxy, we'll use the IDA to get local ground truth. We'll use the remote sensing to get local remote sensing ground truth, and then we'll bootstrap to distant remote sensing measurements and hopefully understand them a lot better. Pontus put this in. It's actually something that's flown down. It was originally in the particles in the heliophysics. Is measure the isotopic gas and dust ratios of very important fundamental lower atomic mass species, deuterium to hydrogen, helium 3 to 4, carbon 13 to 12, O18 to 16, should also be O17 to 16, 22N, the neon ratio and the argon ratio, And if we can measure this in the solids with the delta M we're planning for this IDA, that would be fantastic and tell you an awful lot about how stars burn hydrogen to helium and heavier atoms, and how fast they were doing it in the local environment versus what we think we can see in the inner galaxy, which is a lot higher density by Sag, by the local giant black hole at the center of our galaxy. You would think that those stars evolved a lot faster through a lot more generations of stars, and they should have a lot more heavier atoms. And they should have atoms that are created by hydrogen burning processes and supernova explosions in different ratios than we see. So this is a fantastic idea to go out and measure this with the IDA. I'm hoping we have the delta M resolution to do that. Moving right along. Now we go back to heliophysics. When we were putting these questions together, we were first thinking with kind of the eyes that Mike was thinking, as they belong in astrophysics and maybe planetary. But then we realized that some of these questions are going to look repetitive, also belong in the heliophysics. What is the composition of local interstellar material? What is the gas and dust between the stars? That's certainly an astrophysical question. Astrophysicists study the 100 billion stars in our galaxy. They ask how they got formed out of that gas and dust. Well, heliospheric people also ask that question more locally. They want to know, what is the galaxy, what is it doing to us, our star system, not one of the other 100 billion ones, but ours. But it's an overlapping question because the sun is just one of 100 billion stars. Nothing personal. And then the other question that directly in dust that wound up in the heliospheric section as well is how much local interstellar matter is in the form of dust and how does it interact with the heliosphere? So this is a two-part question. One is, and I'm always cognizant of the fact that the gas to dust ratio, I'm going to say this carefully, we think there's 100 times as much gas mass as there is dust mass in the galaxy, in the ISM. In our solar system, as far as we can tell, that ratio is about 1 to 1. So one of the real simple questions is, how do we lose all, it's hydrogen mainly, that dominates. How do we lose all that hydrogen? Do we throw it all into the sun? Did we blast out 4/5 of the original material into bipolar jets in the very early part of the solar system in the T-Tauri phase? Did we put it into water? What happened to it? So that's a big puzzle. Most of us think it simply just evaporated, got kicked out. And then the second question is, how does it interact with the heliosphere? If there's 100 gas kilograms for every 1 dust kilogram, how is it that the gas from the ISM doesn't re-pollute or re-dominate our system? What is happening to all the hydrogen? And what's happening to all the dust, for that matter? We have the suggestion from the GUC measurements versus the remote sensing measurements that a lot of the dust may not be making it into the solar system from the ISM. So what is the mechanism? Why does it seem to be compositionally selective? What's going on? Okay, those are all the questions. As I said before, it's very likely we could maybe break this very last question into 2 questions if that's necessary. I had to explain it for quite a while. You could write it differently. You could add. Let me show that there are 2 items. Well, there's 1 item, and now I understand too, the radioplasma wave experiment. There was 1 item that came up. Alan Stern pointed out that Mihai has been pushing this idea, or arguing that if we actually could measure dust in the environs of a KBO as we fly by it, then we could actually maybe learn something about the KBO. Now, I pushed back and said is that we didn't see any enhancements for dust in the Pluto system. We didn't see any enhancement in dust around MU69. But Pluto, remember, is a big body with an atmosphere. So it could have been big enough to put out a bunch of dust, but the atmosphere keeps the dust on the planet, as well as the gravity. If we fly by an intermediate-sized object like Quaoar, I believe it has no evidence for an atmosphere, but it could also be big enough to create enough dust around it that we maybe in a flyby, we could capture a little of its dust. And that's an exciting idea. It's a very simple idea.
Casey, I put a comment to that effect earlier up on the STM.
Thank you, good.
Talking about the radial distribution of dust, I said especially around trans-Neptunian planetary bodies.
Yeah, that's great. So I think that's a great piece. That shows you how this workshop has succeeded. I'm sorry, I'm almost out of time and I'm almost done. I'm willing to stay on, by the way, but you guys may need to leave. The other goals of this workshop and this document: input on how dust science operations will occur. If you have anything to say that would, here basically, you saw me already say this. If you have a riff or you want to change slow spinning 1 RPM, different from 20 or 30 degrees cone angle, always on, tell us. If you think the data volume allocation is different, Jamie has already talked to Peter Coleman, who's collecting all the information. If you think it'll be different, I don't think this is going to be controversial, so I won't dwell on it. I think it's low. If you have any comments on the 2 example payloads, but since the IDA is in the basic, This would mainly be is, do you also want to make sure we fly the visible infrared mapper so we get remote measurements? That's what this would be focused on. And finally, if there are any science trades, if you can think of an instrument like the IDA, but for another 5 kilograms, you can measure all the way out to uranium and you can get delta M, I'm totally spitballing here, 0.1 AMU, then you should say it here. I don't think there is such a thing because I think the state of the art is the IDA that we're putting out there as a straw man, but something like that, if you have anything else, or if, for example, you really want to stop the spin for the spacecraft and you want to stare at the galactic center because you think there's dust coming from there, say that. And again, just like Bill has done here, give us your input. We're hungry to get it. We'll talk to you later. Don't be shy. Especially, as I said, for the youngsters, this may sound complicated. It is a little tough even for people who've been doing this for years, but this is where you put your input here. And if you don't say it, it won't happen. So thank you very much for listening. You can see Kirby's already commented and Bill's already commented. And I'm done if anybody wants to take a minute to talk.
I also would encourage more discussion over at the poster session with all the different authors who participated today and will be at the poster session. But Casey, you've done a great job with organizing this team, just as you did last year and the year before, as well as this Google Doc with all the very deliberate questions and the clear statement of what this workshop's trying to do. So thank you.
Thank you, Michael. And one of the, I did point out to the team is that one of the successes of these workshops has been that we got the IDA and the baseline. People like it. Everybody likes it. Okay.
Thank you, Casey. And I just wanted to let everybody know that the link to the poster session, the Gather Town poster session, is in the chat. And thank you everyone for posting your comments in the chat as well.
Okay.
Thank you, everybody. And thank you for your participation and your future inputs.
Thank you.